Some ancient stones don't just sit in place, they click together with a precision that feels industrial, like the rock remembers a blueprint. Edges meet without mortar, seams vanish, and surfaces look measured, not merely carved. So who taught Bronze Age hands to build like this? Lost engineering they tried to hide, or a human technique so advanced we've forgotten how to see it? Across deserts, mountains, and ruined coastlines, we find seams so tight a blade cannot enter, faces so flat they catch light like glass. Massive blocks meet at angles that should betray a mistake, yet they close as if guided by instruments. It looks like machining, it sounds like measurement, and it leaves us with a troubling silence where the method should be. This is a documentary about precision that refuses to behave. In the modern world, tolerances are enforced by gauges, reference surfaces, and inspection, systems that turn craft into repeatable truth. Yet in monuments dated to Bronze Age toolkits, we encounter straight lines held across meters, corners that keep their square, and joints that read like a single cut. So what are we truly seeing when stone looks engineered? Evidence of lost advanced technology, or proof that we still underestimate discipline, time, and technique? The debate is loud because the stakes are larger than a wall or a quarry. If we call it impossible, we invite fantasies of hidden machines and vanished civilizations. If we call it simple, we risk explaining away data that deserves to be measured, not dismissed. Our approach begins where wonder should always begin, with definitions. Flatness is not a feeling, squareness is not a rumour, and precision is meaningless without numbers. A photogenic joint can be tight at the face and open behind, and shadows can turn rough stone into a perfect line. A circular hole can look like industry, yet the mark of a tool is also the mark of a process. And processes leave families of traces, not single miracles. We will follow those traces from the quarry to the finished monument, from the grit that cuts to the hands that guide. We will ask what copper, bronze, stone, and abrasive slurry can do when patience is organised at state scale. We will also ask what they cannot do, because the hardest questions live in the mismatch between material and tool. Granite and diorite do not yield easily, and that resistance is where the story becomes sharp. Along the way, we will confront the most provocative claims without surrendering to them. Drill holes and partial cores will be examined as evidence, not icons. Patterns to be measured, compared, and tested against real mechanics. Transport and lifting will be treated with the respect they demand, because no cut is impressive if the block cannot be moved. And when the argument turns toxic, we will look directly at why, how certainty is marketed, how doubt is punished, and how institutions and algorithms can both distort the same silence. This film is not a hunt for a single forbidden device. It is an investigation into a possibility that is harder to accept, that the lost technology may be a lost standard of workmanship, where measurement was sacred and repetition was the machine. If that is true, the most unsettling discovery will not be what ancient builders possessed, but what we have forgotten to recognize. So watch the light crawl across a granite face, and listen to the joint that refuses to admit error. Somewhere between myth and method, these stones are waiting to be read, 1 millimeter at a time, and by the end the question will remain, but it will be sharper, cleaner, and far more difficult to ignore. From engineered seams around the world to Egypt's granite problem, from drill core mysteries to the logistics of moving mountains, we'll widen the lens until monuments become measurable data. Then we return to the human story, because the final answer may demand more respect than conspiracy. A seam in limestone closes until light cannot enter, until even dust seems unsure where to settle. A blade cannot find purchase, because there is no lip, no step, no forgiving gap. Two stones meet like parts, not rubble, and the contact line reads like a decision. At Giza, surviving casing blocks still hint at vanished perfection, even after millennia of quarrying, earthquakes, and reuse. Their faces align with a confidence that feels measured, as if a reference plane was carried from block to block. The joint lines look planned, then executed, and the eye keeps returning to the same quiet question. In Peru, polygonal walls climb with irregular shapes that still lock tight, turning the hillside into a puzzle that refuses to loosen. Each stone turns, bites, and settles into neighbours without mortar, yet the wall behaves like a single body. The fit looks organic, like river stones pressed together, and still the contact is exact. Around the Mediterranean, megalithic blocks sit with unnerving certainty, their mass made visible by the way they dominate the landscape. Some weigh as much as modern cranes fear, especially when the ground is uneven and the lift is blind. They rest as if lowered into a final position, then never moved again, and the silence around them feels earned. The first question is simple and stubborn. How did they do this? The second question is harder, because it asks what we are really seeing when stone looks engineered. Are we witnessing extraordinary technique applied patiently, or evidence of tools we have not fully accounted for? This film does not begin by choosing a side, because sides are easy and methods are hard. It begins by choosing a method, one that treats awe as a starting point, not a verdict. We will separate what can be measured from what is merely felt, and we will keep those categories from bleeding into each other. Awe is not evidence, but it is a signal, like a spike on an instrument that tells you where to take readings, closer, where to slow down and where to stop trusting first impressions. It tells us which claims deserve a ruler, a microscope, and a repeatable test. Precision is a word that needs boundaries, because it can mean anything from looks neat to meets a specification. In engineering it means flatness, squareness, and parallelism, and it means those properties within known tolerances. It also implies inspection, because precision without verification is only a belief. Flatness asks how much a face deviates from a plane, not whether it looks smooth in raking light. Squareness asks whether edges meet at true right angles, or whether they drift by a degree that the eye forgives. Parallelism asks whether opposite faces keep the same distance across length, because a block can be flat and still be a wedge. Tolerances are the allowed errors in a fit, and they are where craft becomes quantifiable. A tight tolerance is not a compliment, and it is not a mood. It is a measurable constraint that demands method, control, and verification, because small errors accumulate into visible misalignment. When people say these stones are impossible, they often mean the tolerances feel modern, like something expected from a workshop, not a hillside. They mean joints that appear too consistent over long runs, where fatigue should show up as waviness. They mean surfaces that reflect like glass when the sun skims across them. Yet perception is tricky, because stone can look smoother than it measures, and shadows can hide gaps that gauges would find. A joint can be tight on the face and open behind it, especially if the stones are relieved internally. The camera loves the cleanest line, so our job is to chase the average, not the highlight. Machining marks are another loaded phrase because it suggests a specific kind of tool before the evidence is fully read. It can mean parallel striations, regular grooves, or repeating patterns that look like a feed mechanism. It can also mean natural fractures, bedding planes, or later abrasion misread as tool traces. Drill cores enter the debate with even higher stakes, because a cylinder feels like a signature of rotation. A cylindrical core implies a rotating tool and abrasive slurry, where grit does the cutting and the tube simply holds pressure. The spacing of grooves can suggest feed rate and pressure, but only if the surface has not been reworked. But a mark is not a machine, and a groove is not a blueprint. A mark is a clue that must be compared to known processes, including the messy ones that leave ambiguous traces. The same pattern can come from different tools or from later damage, or from the stone itself failing along its crystals. The material sets the difficulty before any human choice enters the story, because not all stone responds to force the same way. Limestone can be cut and dressed with relative speed, especially when it is fine-grained and freshly quarried. Granite and diorite resist in a different way, because they are not uniform, and they do not forgive. Granite is hard, crystalline, and uneven at the microscopic level, a mosaic of minerals with different hardness and fracture behavior. Quartz resists abrasion, feldspar cleaves unpredictably, and mica can peel into thin sheets that complicate a clean finish. Under magnification, a smooth granite face can be a landscape of tiny ridges and pits. Diorite can be tougher still, with interlocking minerals that punish soft metals and blunt edges quickly. It does not yield to simple scraping, and it does not cooperate with casual grinding. If you want a flat plane in diorite, you must remove high points patiently, then check again, then remove more. Bronze is softer than quartz, and copper is softer than feldspar, and that mismatch drives the argument like a wedge. The monuments are often made from the harder stones, and the toolkits we associate with those periods are often made from softer metals. The question becomes not whether cutting is possible, but what combination of abrasion, pressure, and time makes it practical. Mainstream archaeology answers with systems, not miracles, and those systems can be surprisingly sophisticated in plain terms. It points to abrasives like sand, crushed quartz, and emery, because grit can cut what metal cannot. It points to pounding stones, saws with slurry and patient finishing, where the abrasive does the work and the tool guides it. It emphasizes time, labor, and incremental improvement, because technique is an accumulation of small optimizations. It emphasizes that ancient builders could test, adjust, and standardize without modern theory, using simple references like plumb lines, water levels, and straight edges. It emphasizes that skill accumulates across generations, and that institutions remember what individuals cannot. There is also a historical backdrop to that confidence, because large states can sustain specialized labor for decades. Egypt, the Andes, and Mediterranean polities all built bureaucracies that could feed workers, organize teams, and enforce standards. When a monument is a national project, precision becomes a political resource, proof that the center can command the margins. Alternative theories begin from the same surfaces and reach elsewhere, because the emotional impact of tight joints is real. They propose lost technology, unknown tools, or knowledge later erased, and they argue that some results exceed plausible hand methods. Their strongest versions focus on repeatability and scale, asking how possible becomes routine across entire complexes. Some versions invoke advanced machines, because machines explain speed and consistency in a single gesture. Some invoke forgotten high cultures, because a vanished lineage explains why the record feels discontinuous. Some invoke outside intervention, though that claim often outruns the evidence, and it can distract from what is actually measurable. Between these narratives sits the real stake, and it is heavier than the stones themselves. The monuments are real, heavy, and precisely placed, and they demand an explanation that respects both physics and history. The question is not whether they exist, but what process produced them, and what that process implies about human capability. If the mainstream is correct, then we have underestimated human ingenuity in the most literal sense. We have underestimated what disciplined labor and abrasive science can achieve, even with simple tools and relentless checking. We have underestimated the sophistication of ancient measurement, including the social systems that make measurement matter. If the alternative is correct, then history has missing chapters, and missing chapters are not a small correction. Those chapters would change how we read progress, because they would suggest peaks and collapses rather than a smooth climb. They would force us to ask who benefited from forgetting, and whether forgetting can happen without anyone intending it. This debate persists because the evidence is uneven, and uneven evidence invites uneven stories. Some stones show rough work beside refined work, as if different crews or different budgets touched the same wall. Some sites show clear tool traces beside surfaces that defy easy explanation, and the contrast itself becomes part of the mystery. It also persists because the conversation is often poisoned by tone before it is tested by data. Skeptics hear arrogance in every extraordinary claim, as if wonder is a threat to competence. Believers hear denial in every ordinary explanation, as if caution is a cover for dismissal. In that noise, careful questions can sound like attacks. Our approach will be calm, evidence-forward awe, because awe can coexist with rigor when it is disciplined. We will not mock questions that begin with wonder, because wonder is often the first honest reaction. We will not accept answers that cannot survive measurement, because stories that cannot be tested are not explanations. We start with what can be checked on site, because stone preserves its own audit trail if we learn how to read it. We look at joints, faces, corners, and the geometry of placement, including how courses rise and how blocks meet at turns. We ask what tools could make those outcomes, and at what cost in time and organisation. We follow the stone back to its origin, because quarries preserve the first decisions and the first mistakes. They hold extraction scars, wedge holes, and half-freed blocks that still cling to bedrock. They show what was attempted, what failed, and what was abandoned when the fracture ran wrong. We trace transport routes because logistics leave fingerprints, and those fingerprints are often larger than the tool marks. Ramps, sledges, waterways, and roads are not side stories because they determine what size blocks are worth cutting. They are the engineering that makes the cutting matter, and they reveal the constraints builders accepted. We examine tool marks with discipline, because the surface is a record of motion. A chisel line has a rhythm, and that rhythm can show direction, spacing, and the angle of attack. A saw cut has a signature, and a pounding stone leaves a different texture than a metal edge, especially when grit is involved. We compare claims to experiments because experiments convert imagination into bounded possibility. Modern teams have cut granite with copper saws and abrasive slurry, and the results can be measured for kerf width and surface character. Others have drilled with tube drills and sand, then measured the results for groove spacing and taper. Experiments do not prove the past, but they bound the possible, and that boundary is valuable. If a method works once, it becomes plausible, even if it is slow and punishing. If it cannot work at all, or if it produces a different signature, then the claim must change. We also watch for the limits of reconstruction, because a controlled test is not a monument-scale workflow. A lab is not a quarry face in heat and dust, where grit contaminates everything and fatigue changes technique. A short demonstration is not decades of institutional practice, where teams learn, specialize, and standardize. Measurement is the bridge between wonder and argument, and it is more than a single instrument. A straight edge reveals a plane, but only where it touches, and only if it is truly straight. Feeler gauges reveal gaps, and laser scans reveal curvature that eyes cannot see, turning surfaces into maps of deviation. Yet measurement can mislead if it is selective, or if it is taken from the most photogenic stone. A single perfect joint does not represent an entire wall, especially if that joint is near a doorway or a ceremonial face. A single rough block does not erase a polished face, especially if the roughness is hidden from view. So we will look for patterns across many stones, because patterns are harder to fake and easier to interpret. We will ask whether precision clusters in certain zones, such as corners, thresholds, or load-bearing points. We will ask whether it correlates with function, status, or chronology, because priorities leave statistical traces. We will also ask why certain features repeat across continents, because repetition can be either profound or mundane. Polygonal fits appear in more than one culture, and massive blocks appear in more than one era, even when the society is not connected. Convergence can mean shared ideas, but it can also mean shared constraints driving similar solutions. It can also mean we're projecting the same modern expectations onto different traditions, reading intention where there is only outcome. A tight joint can be structural, but it can also be aesthetic or symbolic, or simply the result of fitting stones until they stop moving. The question is not whether it looks impressive, but what problem it was solving. The emotional hook remains because the fit still feels uncomfortable, and discomfort is a kind of data. Stone is supposed to be stubborn and imperfect, and here it behaves like it was negotiated into place. The seam looks less like a crack and more like a boundary between decisions. When a joint is tight, it suggests control over shape, including the ability to remove high spots without ruining the whole face. When faces are parallel, it suggests control over measurement, because parallelism must be checked across distance. When corners meet cleanly, it suggests control over squareness, because the error shows immediately at an edge. Those controls do not require electricity, but they do require standards, reference surfaces, and repeated checking. They require a culture that values precision enough to pay for it, because precision is expensive in time and attention. They also require training, because the hand must learn what the eye cannot reliably judge. That is why these monuments matter, beyond beauty and beyond myth, and beyond the thrill of the unexplained. They are not only art or religion, though they are both. They are records of capability, organization, and the will to impose geometry on nature, even when nature resists. They also matter because they challenge our timeline instincts, which prefer a clean story of progress. We expect roughness early and refinement later, because that is how many technologies behave. These stones sometimes reverse that expectation, and the reversal forces us to ask whether we are dating skill correctly. In some places, the oldest work looks the most exact, as if the first builders arrived with a mature tradition. In other places, later repairs look cruder than the original, as if knowledge narrowed or budgets collapsed. That inversion fuels suspicion and invites speculation, because it resembles loss rather than growth. But suspicion is not a conclusion, and it cannot substitute for careful sorting of layers. It is a prompt to ask better questions, and to ask them in the right order. What is original? What is restored? What is refaced? And what is simply weathered by wind, salt, and time? We will keep returning to the same central question, because it is the hinge on which the entire debate turns. Do these monuments prove lost advanced engineering, or do they reveal how much we still underestimate human technique? The answer may not be a single word, and it may vary by site. To answer, we must define what counts as advanced, because advanced can mean different things in different contexts. Is it the tool itself, or the outcome it produces? Is it speed, repeatability, and scale, or is it the ability to achieve a tight fit at all, even slowly? We must also define what counts as hidden, because disappearance does not always require a plot. Some knowledge disappears without conspiracy, when economies collapse, when patrons change, and when guilds dissolve. A technique can vanish simply because it is no longer worth teaching, and the last experts die without apprentices. Yet the phrase forbidden engineering persists because it captures a feeling, and feelings often point to real social dynamics. It suggests that certain explanations are dismissed too quickly, and that curiosity is treated as threat. It also asks a sharper question: who gets to decide what is reasonable before the measurements are taken? This film will test that feeling against the record because the record is stubborn and specific. We will listen to archaeologists who map quarries and catalogue marks and who can tell a chisel scar from a natural spool. We will listen to engineers who think in tolerances and process windows and who know what consistency costs. We will listen to craftspeople who cut stone today because their hands understand friction, chatter, and grit in a way diagrams cannot. They know what a surface costs in time, and they know how quickly a tool degrades when the stone is unforgiving. They also know the quiet truth that possible can still be brutally inefficient. We will also listen to those who argue for missing tools, because skepticism should be applied in both directions. We will ask them for measurements, not just impressions, and for comparisons that survive scrutiny. We will ask what predictions their theory makes at the quarry, where the process begins and where mistakes are preserved. Because a theory must do more than explain a finished wall, which is the easiest place to be seduced. It must explain waste, errors, and learning curves, including why some blocks are perfect and others are not. It must explain why a culture would choose one method over another, and what constraints forced that choice. The stakes are not only academic, because stories about the past shape what we believe about ourselves. They shape how we credit ancient people, and whether we see them as engineers or as beneficiaries of mystery. They shape how we teach history, and how we imagine progress, and what we think human communities can build with limited means. If we assume the past was incapable, we shrink human potential, and we make innovation look like a modern monopoly. If we assume the past had secret machines, we risk erasing the labour that is visible everywhere, from quarry scars to transport paths. Either error costs us something, and both errors are tempting, so we stand in the seam between two stones and slow down, because speed is the enemy of interpretation. We let the joint speak first, and we let the material, the mark, and the measurement lead. We treat the wall not as a riddle to solve quickly, but as a document written in mineral and force. From here, the journey becomes specific, because specificity is where claims either strengthen or break. We move from global montage to a test case that anchors the argument, and we choose a place where the record is vast. We go to the place where stone became a language of power, and where precision was made public. Egypt is where precision is not an accident, and not merely a byproduct of careful hands. It is a statement carved into architecture, repeated at a scale that turns craft into policy. It is where the question becomes unavoidable, because the scale is absolute, and the surviving evidence is extensive. Next, we follow the stone to the Nile, to the quarries, and to the monuments that define the debate. We begin where the world always begins this argument, because the images have become a global shorthand for impossibility. We begin in Egypt, and we begin with the stones that still refuse a blade. Some stones at Giza do not just sit in place, they seem to lock into reality with a precision that feels modern. In harsh sunlight, the joints become razor-thin shadows, and the surfaces catch the sky like muted mirrors. Chapter 1 separated awe from evidence, then demanded measurement over mood. Chapter 2 keeps that method and changes the material, because the material itself changes what is physically plausible. When the stone changes, every assumption about tools, labour and time must change with it. Limestone built most of the plateau, and limestone is forgiving when freshly quarried. It can be cut with copper, scraped smooth, and corrected late in the process. Granite and diorite are different problems because their crystals fight every cut and resist every casual shortcut. Granite is a mosaic of quartz, feldspar and mica, and quartz sets the difficulty. On the Mohs scale, quartz sits around 7, which is why it scratches glass and shrugs off softer metals. Feldspar is slightly softer, mica cleaves in sheets, yet the quartz grains dominate the feel of the stone. Diorite is tougher and more interlocked, and it punishes soft edges and casual abrasion. Its dark minerals knit together like a dense fabric, so impacts bounce and edges crumble. When you see diorite shaped cleanly, you are seeing persistence made visible. This hardness mismatch drives the controversy. Because Egypt's early metal tools were copper and bronze, copper can shape wood and soft stone, but it struggles against quartz without help. Even bronze, harder than copper, still loses the direct contest with crystalline silica. So the argument shifts from blades to systems, where abrasives do the cutting and tools guide pressure. Sand, crushed quartz, and emery become the real cutting edges, because hardness is not a rumour. In that world, the metal is a frame, and the grit is the tooth. We start where Egypt's hardest stones begin, because origin constrains method. The granite that reaches Giza largely comes from the Aswan region, far upriver. That distance matters, because it forces decisions about block size, risk, and acceptable waste. Aswan is not just a quarry, it is a training ground for extraction and control. The bedrock is exposed in broad, sun-bleached slabs, and the surface carries scars like a record of decisions. It preserves unfinished blocks and trenches that show how stone was separated from living rock. Quarrying hard rock demands planning, because fractures are expensive and unpredictable. Granite has joints and micro cracks that can run like hidden faults, and a bad split can ruin a block late. A wrong crack wastes weeks and exposes what the builders could not control. In Aswan, you can still see channels cut around intended blocks, and you can imagine the rhythm of work. Dolerite pounders strike again and again, bruising the surface into a shallow trough. The sound would have been sharp and repetitive, a steady percussion across the riverbank. Extraction is not only about breaking stone, it is about guiding the break. Workers could exploit natural fissures, deepen them with pounding, and open them with wedges. Wooden wedges soaked with water can swell and apply slow pressure, turning time into force. From Aswan, granite had to move by river, then by sledge, then by lever and ramp. Transport is part of the toolkit, because it decides what sizes are worth cutting. A block that cannot be moved is not a block, it is an abandoned intention. The Nile is the silent conveyor in this story, and its seasons shape the schedule. High water can bring barges closer to loading points, while low water exposes sandbanks and delays. The river also demands planning, because a cargo of stone is unforgiving when balance fails. At Giza, the public story is often the pyramid, but the granite story is broader. It includes temples, pavements, interior chambers, portcullis blocks, and thresholds. Granite appears where strength, symbolism, or permanence mattered enough to justify the cost. We narrow to a test case with measurable claims, because the debate needs anchors. Giza offers preserved precision, preserved roughness, and preserved transitions between them. Those transitions are crucial because they show where effort increased and where it deliberately stopped. The Great Pyramid's casing is mostly gone, but surviving casing stones still matter. They show finished faces and joint lines that were meant to be seen. In close view, the faces are not merely smooth, they are controlled, as if corrected until the light behaved. Casing precision is not the same as core masonry, and Egypt used both deliberately. The core can be rough and stepped because it is hidden and it carries mass. That contrast is not a failure. It is a strategy that spends labour where labour is visible. Finished faces demand different tolerances because they define straight lines across long distances. A small drift becomes visible when it repeats course after course. The human eye is sensitive to cumulative error, especially along edges that catch the sun. This is where the central question becomes practical rather than mystical. Do these results require lost advanced engineering, or do they show disciplined craft scaled up? The answer cannot be guessed from a photograph, because photographs compress depth, texture, and context. We must also be honest about variation, because variation is part of the evidence. Some joints are tight on the face and relieved behind, which changes what fit means. A joint can be a display of control on the surface and a labour-saving compromise in the interior. A tight face joint can be aesthetic, weather-resistant or symbolic, and still be rational. A relieved interior can save labour while preserving the appearance of perfection. It can also reduce binding during placement because a slight hollow gives room for adjustment. So we ask where precision clusters and where it relaxes, because function predicts effort. Corners, thresholds, and ceremonial surfaces often receive the most controlled finishing. Places that define an axis or frame a ritual are where error becomes unacceptable. We also ask what the builders could verify, because precision requires inspection. Verification can be simple and still powerful when it's applied relentlessly. A simple tool, used thousands of times, can outperform a complex tool used carelessly. Plumb bobs establish vertical truth, and they do not care about belief. A weight on a cord finds gravity, and gravity is the same in every dynasty. When a wall is checked repeatedly, the cord becomes an uncompromising judge. Squares establish right angles, and they reveal error quickly at edges and corners. A small gap at the heel of a square is a warning, and it forces correction early. Over long runs, that early correction prevents drift from becoming visible. Water leveling establishes a horizontal reference across distance, even without complex math. A water surface seeks level, and a channel or trough can extend that fact across a worksite. Sightlines and stretched chords extend that reference, turning points into planes. These tools do not cut stone, but they dictate what must be removed. Measurement creates a target surface, then labour and abrasion chase that target. The target is invisible until it is checked, and then the stone must yield to the check. Now we move from the pyramid's skin to its neighbourhood, where granite appears in heavy finished architecture. The Valley Temple complex becomes a pressure test for handling and levelling. Here, the stone is not only shaped, it is seated, aligned, and made to feel inevitable. The Valley Temple uses massive blocks, including granite casing over a limestone core in places. Some blocks are megalithic in scale, and their placement is not casual. The walls read as deliberate geometry, even when the blocks are irregular in size. Mass matters because it changes what adjustment means. A small correction on a multi-ton block is a logistical event, not a quick tap. The force required is not just muscular, it is organisational, because many hands must act as one. Alternative narratives focus here, because the blocks look seated and squared like machine-set parts. Mainstream narratives answer with bedding, shimming, levering, and repeated checking. The disagreement often hides in the word repeated because repetition is where precision is purchased. Levelling a foundation is not a single action, it is a process of reference and correction. Builders can dress contact points, add packing, and reseat until the stone stops rocking. A block can be tested, lifted slightly, corrected, and tested again until it behaves. Packing does not have to be crude, and it does not have to be permanent. Thin stone shims can be placed where needed, then concealed by later courses or finishing. Bedding layers can also distribute load, reducing stress points that would crack stone over time. The question becomes whether the observed flatness and squareness exceed plausible workflows. That depends on what is measured, where it is measured, and how often it repeats. A single perfect corner is impressive, but a pattern of controlled corners is a system. We keep returning to the same rule from Chapter 1. A photogenic joint is not a statistical sample, and a rough patch is not a refutation. The site must be read like a dataset, with attention to selection bias and preservation. So we map the site by function, because function predicts tolerance. Exterior ceremonial faces invite precision, while hidden backing stones can remain irregular. The builders could spend hours on a visible plane and minutes on a buried surface. We also map by chronology and repair, because later interventions can degrade earlier standards. A reused block can carry old precision into a new wall that is less exact. Erosion, earthquakes, and human reuse can blur what was originally sharp. Granite at Giza also appears inside the Great Pyramid, where conditions change again. Interior granite blocks are not about weathering, they are about load and stability. In the dimness, the stone is not a facade, it is a structural decision. The king's chamber uses granite beams and walls, and it concentrates attention on right angles and planes. Whether those planes are truly flat is a measurable question. In low light, even slight waviness can disappear, which is why measurement must replace impression. Granite beams above the chamber stack in relieving spaces, and their role is mechanical. They redirect weight away from the chamber ceiling, spreading stress into the surrounding masonry. The choice of granite here is not decorative. It is a response to compression and failure. Granite portcullis blocks in the ascending systems add another constraint. They must slide and seat, which implies controlled surfaces and predictable geometry. A stone that jams is a stone that defeats its own design. A sliding stone does not require modern machining, but it does require repeatable clearance. Clearance demands measurement, and measurement demands reference tools that can be trusted. It also demands an understanding of friction, because roughness turns motion into resistance. Now we place Egypt's toolkit on the table, because the toolkit is the battleground. Copper chisels exist, but their limitations must be stated without exaggeration. They are real tools in a real economy, and their performance can be tested. Copper edges deform quickly against hard crystalline stone, especially quartz-rich granite. That does not make them useless, but it changes their role to trimming and soft work. Copper can dress limestone, cut gypsum mortar, and refine edges after abrasive work has done the heavy removal. Work hardening complicates the picture, because copper can become harder when hammered, but it also becomes brittle, and it still cannot outscratch quartz in a direct contest. The practical result is frequent resharpening, frequent replacement, and careful choice of where the chisel is used. Dolerite pounders appear in the archaeological record, and they match the quarry evidence at as one. Dolerite is a hard, dense, igneous rock, and it survives impacts that would shatter softer stone. Pounding can rough-shape granite, but it is slow, and it leaves a signature. That signature is a field of shallow pits and bruises, a texture that looks like controlled violence. It is not a saw cut, and it is not a polished plane, yet it is the first step. Once a surface is knocked down, grinding can begin, and grinding is where accuracy can emerge. Stone hammers and mauls can drive wedges, knock down high spots, and prepare surfaces for grinding. They are brute tools that become precise only when guided by measurement. Without a reference line, pounding is only destruction, but with a reference line it becomes shaping. Saws and drills shift the logic because they can carry abrasive slurry into a controlled path. In that model, metal is a holder and a guide, not the cutting edge. The cutting happens where hard grains are trapped and dragged, scratching the stone one pass at a time. A copper saw with sand can cut granite, and experiments show it can work. The cost is time, grit, and constant management of wear and slurry. The saw must be kept straight, the abrasive must be replenished, and the kerf must be cleared so grains keep biting. The abrasive itself is not generic sand in every case, and that matters. Quartz sand can cut, but crushed quartz or emery can cut faster because of grain shape and hardness. Grain size also changes the finish. Coarse grains remove material, fine grains refine planes. Tube drills with abrasive can produce circular holes and leave spiral or concentric striations. The spacing of grooves can imply feed rate, but only if the surface is original. A reworked hole can erase its own history, which is why context and preservation are everything. Rotation also raises questions about control, because a drill must stay centered and stable. A simple bow drill can rotate a shaft, and a weighted drill can add pressure, yet the abrasive does the cutting. The visible record is not the wood or copper, it is the pattern left in stone. Wooden sledges, ropes, levers, and rollers belong in the same sentence as chisels. They are not supporting characters because moving stone is the largest energy expense. A perfect block is meaningless if it cannot be delivered, positioned, and set without damage. Friction is the hidden opponent in every transport scene, and it can be managed. Wetting sand can change how a sledge rides, and prepared tracks can reduce losses. Coordination matters as much as strength, because uneven pulling twists loads and breaks gear. Egypt also had organisation, which is a technology of its own. A state can sustain specialists, standardise methods, and enforce tolerances through inspection and hierarchy. When crews repeat the same tasks, muscle memory becomes a form of precision. That institutional context matters, because precision is expensive and must be valued. When precision becomes political and sacred, it becomes worth paying for in labour. A temple face is not just stone, it is authority made permanent. Yet the controversy persists because some granite surfaces look unusually straight and unusually square. The claim is not only that it is possible, but that it looks routine. When a visitor sees multiple examples, the mind asks whether chance can explain the consistency. Routine precision across many blocks would imply a stable process window. A stable process window implies repeatable measurement, training, and quality control. It implies that workers knew what good enough meant, and that someone had the authority to reject errors. So we ask what exactness means in this setting, because words can inflate. Straightness can mean visually straight, or it can mean deviations measured in millimeters. A face that looks perfect at 2 meters can reveal waves when checked with a long straight edge. Right angles can be checked with simple squares, but large-scale squareness is harder. A small angular error grows into a visible drift over long runs. That is why corners and doorways matter so much, because they concentrate geometry into a readable frame. Flatness is the most seductive claim, because a polished plane feels like a machine signature. But flatness must be tested with straight edges, feeler gauges and modern scans. A polished surface can be glossy and still be subtly convex or concave. When modern surveys do find high precision, the next question is always the same: how much of that precision is local, and how much is systemic across the structure? A single plane can be refined by patient grinding, yet a building demands that many planes agree. We also ask how finishing was prioritized, because finishing consumes time. A face can be dressed to a plane while adjacent faces remain rough, if only one face is seen. That selective finishing is not deception, it is efficient allocation of effort. This is why core masonry and finished faces must be discussed together. The same monument can contain both, and that mix can look like contradiction when it is strategy. The builder's goal is not uniform perfection, it is controlled appearance and controlled load paths. At Giza, the best work often sits where it matters most to alignment and display. The rougher work often sits where it is buried, buffered, or structurally redundant. That distribution is a clue, because it suggests intentional priorities rather than random capability. That pattern supports mainstream explanations, but it does not end the debate. The debate shifts to the upper limit, where the best examples challenge modern expectations. If the best work is extremely good, then the process behind it must be extremely disciplined. We do not resolve that tension by choosing a side early. We resolve it by narrowing claims to what can be measured and compared to known processes. The goal is not to defend a narrative, but to understand what the stone is actually saying. So we return to the quarries, because quarries preserve the first steps and the failures. If advanced methods existed, they should leave consistent extraction and cutting signatures. A method that works at scale leaves patterns, because scale amplifies habits. We return to tool marks, because tool marks are motion frozen in stone. Pounding textures differ from saw kerfs, and grinding differs from chisel chatter. Under raking light, a surface becomes readable, and the direction of work can emerge like grain in wood. We return to logistics because logistics reveal what was feasible at scale. If granite was moved routinely, then the society solved friction, coordination, and scheduling. It also solved risk because every transport run carried the possibility of catastrophic loss. And we return to geometry, because geometry is the language that ties everything together. A culture that can hold lines and angles can build monuments that feel inevitable. The more consistent the geometry, the more the monument reads like a single thought. Still, one boundary remains, and it is the boundary that will carry us into the next chapter. Precision on flat planes is one kind of achievement, but circularity is another. A circle is not only a shape, it is a demand for continuous control. A straight edge can chase a plane, and a square can chase a corner, with patience and grit. A clean drilled hole implies rotation, feed, and control that feel different. It implies that the tool moved smoothly, and that the abrasive kept cutting without wandering. So we end Chapter 2 with a controlled pivot from faces to voids. We move from granite plains at Giza to holes that look like they were drilled. The evidence stops being a surface and becomes an absence, a negative space that still carries a signature. The central question stays the same, but the evidence changes shape. Do these monuments prove lost advanced engineering, or do they reveal underestimated human technique? If we assume the past was simple, what do we miss when the stone refuses simplicity? The most forbidden engineering may not be a hidden machine. It may be a forgotten respect for disciplined craft, where time, measurement, and materials were treated as sacred. When patience is organized and repeated, it can look like magic to anyone who arrives later. Next, we follow the circle, because circles leave numbers behind. We follow the drill marks, the cause, and the claims that a simple tool cannot explain them. A drilled hole in granite feels like a confession. an admission that someone brought rotation, pressure and control to one of Earth's stubborn stones. The camera lingers on a circular void, and the mind supplies the rest, because circles in hard rock read like industry. Viewers see cylindrical holes, partial cores, and smooth inner walls that appear too regular for casual handwork. Under raking light, the walls flash with faint bands, and the surface seems to carry a disciplined rhythm. They see spiral striations that resemble a feed mechanism advancing at a steady rate. In close-up, those spirals look like the ghost of a screw thread, as if a tool descended with mechanical certainty. Alternative theorists treat these holes as the most provocative evidence in the entire debate. If the marks are truly machine-like, then the tool story must expand, because the stone appears to remember a machine. Our method stays the same from the earlier chapters, even when the visuals feel overwhelming. We separate what looks precise from what measures precise, then we compare marks to known processes. A hole is not just an opening, it is a record of motion, because the tool must repeat the same path thousands of times, and repetition leaves signatures. Granite raises the stakes because quartz grains resist soft metals, and quartz is not a minor ingredient. In many granites, quartz makes up a large fraction of the rock, and it brings a hardness near 7 on the Mohs scale. That hardness mismatch makes the hole feel impossible, until we describe how stone drilling actually works. The key is that hardness is not the only variable. Geometry, pressure, grit, and lubrication can rewrite what seems plausible. Hard stone drilling is usually abrasion, not cutting in the knife-like sense most people imagine. The abrasive grains scratch and crush the surface, while the tool mainly holds shape and pressure, acting like a moving scaffold. Copper can work against granite if copper is not the cutting edge. Copper can be a carrier that traps quartz sand, then drags it through the stone, letting the harder mineral do the damage. Rotation supplies repeated contact, pressure keeps grains engaged, and slurry clears debris so fresh grit can bite. Without clearing, the hole polishes and stalls, because the interface becomes a slick paste of worn particles. Modern diamond drills cut by embedded hardpoints, and they thrive on high torque and rigid alignment. Ancient-style drills cut by loose hard grains, which means the process is slower but still physical, and still capable of surprising regularity. This chapter is a close-up investigation of the circle. We treat each groove as a clue, not as a verdict. First, we define what viewers are actually looking at, because a drilled hole is not a single category. A drilled hole can be straight or tapered, smooth or pitted, and clean or reworked, and each trait narrows the tool story. A tubular drill leaves a ring-shaped cut and can produce a core. A solid drill grinds the full diameter and leaves no core at all, which changes both the waste material and the wall texture. A core sample is persuasive because it implies a tube, and a tube implies intention. A tube implies a controlled diameter, and a controlled diameter implies engineering choices that feel closer to machines than to improvisation. But a core is not automatically evidence of advanced machinery. A simple copper tube can create a core if abrasive slurry does the cutting, and if the tube is kept rotating with steady pressure. We also define striations with care, because the word can smuggle in assumptions. Striations are grooves or ridges on the hole wall, created by grit, wobble, changing pressure, and the way debris is carried away. Spiral striations can form when the drill rotates and advances at the same time. The spiral can look like a screw thread even without a screw feed, because any continuous descent creates a helix. A repeating groove spacing can be produced by human rhythm, not just by gears. A pump drill stroke can advance slightly each cycle, leaving periodic bands that mimic a measured step down. A bow drill can also create periodic patterns if the operator pauses, resets, or changes pressure. The stone records those micro-decisions as texture, and granite preserves them with stubborn fidelity. Now we explain the basic tool families that could exist in ancient contexts, because plausible tools must be buildable and maintainable. The simplest is a bow drill with a wooden shaft and a stone or metal bit, guided by a handheld capstone. A bow drill converts back and forth motion into rotation through a cord, and its speed can be deceptively high. It can spin quickly, but it struggles to maintain constant downward force, especially as the hole deepens and friction rises. A pump drill adds a flywheel and a vertical spindle, turning pulses into smoother rotation. It stores energy and stabilizes the cut, which can reduce chatter and create a more uniform wall finish. A weighted drill increases pressure by adding mass near the spindle, letting gravity contribute to the force budget. More pressure can increase cutting rate, but it also increases heat and binding, and it can make alignment failures more dramatic. The tubular drill is the key suspect in the drill core mystery because it explains the core without demanding exotic materials. A copper or bronze tube, rotated with slurry, cuts a circular kerf and frees a core like a hollow punch driven by grit. The tube does not need to be hard in the way steel is hard. It needs to be round enough, stiff enough, and replenished enough to keep abrasive at the cutting edge, even as the metal itself wears and thins. Sand and crushed quartz are the likely abrasives in many regions, and their availability matters at scale. Emery is harder and sharper, and it can accelerate cutting if available, but it must be sourced, transported, and sorted. Water matters because it carries grit, cools the interface, and flushes swarf out of the kerf. A dry hole clogs, overheats, and turns cutting into polishing, because the abrasive loses its bite. Slurry consistency changes the signature in ways that are easy to miss on casual inspection. Thick slurry can trap grains and cut aggressively, while thin slurry can wash grains away and slow progress, leaving a smoother but less efficient surface. Grit size changes both speed and finish, and it changes the look of the wall under light. Coarse grains remove material faster and leave deeper scratches, while fine grains refine and blur the pattern, making the surface look more machined than it is. Rotation speed changes how scratches overlap and how the eye interprets order. Faster rotation can average out irregularities, while slower rotation can leave more distinct separated grooves that read as deliberate scoring. Wobble changes everything, because it converts rotation into a wandering orbit. A slightly off-center drill can widen the hole, create uneven striations, and produce a spiral that looks engineered, even when it is accidental. Pressure that varies with each stroke can create banding that resembles a feed rate. Even a skilled operator produces cycles of force, especially with a pump drill, because the body is a metronome as much as it is a motor, so the first tension emerges, and it is the tension that fuels the entire controversy. Marks that look like machine feed can also be the fingerprint of human rhythm interacting with abrasive physics, and Granite does not label the difference. We now address the most cited claim from alternative literature, because it is specific enough to test. Some holes appear to show a uniform spiral pitch that implies high feed rates, as if the tool dropped quickly with each revolution. High feed rate means rapid advance per revolution, and that is a demanding requirement in hard stone. If the pitch is truly consistent and steep, it would demand unusual power and control, plus a way to keep the tube from binding. But pitch must be measured carefully, not inferred from a dramatic photograph. A spiral can be misread if the surface is chipped, if lighting exaggerates ridges, or if the hole was later cleaned, sharpened, or filled with dust that hides defects. A drilled hole can also be reamed, scraped, or widened after the initial cut, especially if it must accept a peg. Secondary work can overwrite the original signature and create false regularity, leaving a hybrid wall that belongs to more than one operation. Context matters because provenance matters, and isolated details can mislead. We ask where the hole is, what stone it is in, and what the surrounding tool marks show, because a hole is part of a workflow, not a standalone miracle. If a hole sits near a joint or a fitting surface, it may be functional and finished with care. If it sits in a quarry or an unfinished block, it may be part of extraction, where speed and leverage matter more than beauty. Ancient holes can be for dowels, clamps, lifting points, or alignment pegs, and each use leaves different expectations. Different purposes imply different tolerances and different finishing effort, and they also imply different drilling angles and depths. A lifting hole can be rough inside if it only needs to hold a rope or a wooden toggle. A dowel hole can be more precise if it must seat a peg without cracking, because a tight fit can split granite along hidden weaknesses. Now we compare what is claimed to what is documented, because the ground truth is the archaeological record. Egyptian sites preserve copper tools, stone pounders, and evidence of abrasive use, and they show a broader culture of grinding and polishing. The archaeological record does not show steel drill bits or hardened machine parts from the relevant periods. That absence does not prove impossibility, but it sets a constraint, because complex systems tend to leave complex debris. The record does show that abrasive cutting was understood, and it appears in multiple contexts. Saw marks, grinding traces, and quarry scars align with a slurry-based workflow, where material is removed by countless microscratches rather than single decisive cuts. So we move to experimental archaeology, because experiments convert arguments into measurable outputs. We ask what has been replicated and what remains difficult, and we pay attention to the conditions that make results succeed or fail. Modern experimenters have drilled granite with copper tubes and quartz sand, and the results are not merely symbolic. They have produced holes and cores that resemble ancient examples in broad character, including taper, wall texture, and the presence of circular kerfs. These demonstrations support plausibility at the level of physics, which is a meaningful threshold. Abrasion works, copper can guide it, and cores can form without advanced metallurgy, because the abrasive is the true cutting tool. But replication is not the same as explanation at scale, and scale is where romance meets accounting. A single hole in a controlled setting does not equal thousands of holes across a major building program, with deadlines, supervision, and variable stone quality. Scale introduces logistics of grit supply, toolware, labour training, and quality control, and each factor compounds the others. It also introduces fatigue, which changes pressure control and increases errors, and fatigue is a silent force in every pre-industrial project. Experiments also reveal the hidden cost that a photograph never shows. Tubes wear and deform, slurry must be renewed, and progress can be slow when quartz grains dull, because dull grit slides instead of biting. Some experiments struggle to reproduce the most dramatic reported feed rates, especially in tougher granite. When speed is forced, the tool binds, the hole wanders, or the tube collapses, and the failure modes look exactly like what physics predicts. That does not automatically validate advanced technology, because the measurement itself may be the weak link. It may indicate that the reported measurements are wrong, selective or taken from altered surfaces, where later damage exaggerates a spiral. It may also indicate that ancient specialists developed better process control than casual tests achieve, and specialization is an ancient technology in its own right. A trained crew can outperform a demonstration by orders of magnitude because they learn how to manage slurry, pressure, and alignment minute by minute. So we define what would count as extraordinary evidence, and we define it narrowly. Extraordinary does not mean impressive, because impressive can still be achieved by slow abrasion, steady hands, and a great deal of time. Extraordinary would mean consistent high feed rates across many holes in hard granite, not just one celebrated example. Extraordinary would mean uniform pitch and depth that resists alternative explanations, even when measured by independent teams under consistent lighting and magnification. Extraordinary would mean tool materials or tool geometries not supported by fines, especially if they imply hardened edges or complex bearings. Extraordinary would mean a signature that cannot be produced by slurry abrasion under any reasonable parameters, including wobble, chatter, and grit variation. We also set criteria for documentation, because claims live or die by measurement. Measurements must include hole diameter, taper, depth, groove spacing, and surface condition, and they must be tied to clear photographs with scale. Measurements must note whether the hole is unfinished, damaged, or reworked, because those states change the wall. A broken edge can mimic a groove, and a later cleaning can sharpen patterns, making them look more intentional than they were. We also ask for statistical sampling, because a process is defined by variation. If only the best-looking holes are shown, we are not seeing a process, we are seeing a highlight reel, and highlight reels are designed to persuade. A real workflow produces variation, even when executed by experts with jigs and routines. If a site shows only perfect holes, that itself would be unusual and would demand explanation, because perfection at scale is expensive in any era. Now we return to the emotional power of the drill core, because emotion is part of how evidence is received. A core feels like a modern artifact because it resembles industrial coring, and the resemblance triggers a modern mental template. But industrial coring is defined by hardened bits, high torque, and rigid frames that suppress wobble. Ancient coring could be defined by patience, abrasive replenishment, careful alignment, and the quiet discipline of repeating the same action for hours. The difference matters because it changes what the evidence implies, even when the geometry looks similar. Similar outcomes can emerge from different tool chains when the physics is shared, and abrasion is a universal language. We also address a common misunderstanding, because it appears in almost every public argument. A soft metal tool does not need to be harder than the stone if the abrasive is harder. and the abrasive is what contacts the granite most aggressively. In abrasive drilling, the tool is a delivery system for grit, not a blade. The grit is the cutting edge, and the stone fails by microfracture and scratching, which is slow but relentless when pressure and motion are sustained. This is why copper saws can cut granite with sand, and why the kerf tells a story. The copper wears, but the sand does the work, and the kerf records the abrasive path as a faint granular handwriting. So the question shifts again, from possibility to interpretation. It becomes less about whether copper can cut granite, and more about whether the observed regularity demands mechanized feed, with a controlled advance per revolution. Mechanized feed would leave a distinctive consistency across many samples, not just a few dramatic close-ups. Human feed would leave subtle irregularities, pauses, and changes in pitch, especially where the operator recharges slurry or corrects alignment, yet human irregularity can be smoothed by high rotation and fine grit, and that is where perception can be fooled. A stable pump drill with a flywheel can average motion into something deceptively uniform, because the flywheel resists sudden changes. We also consider wobble as a generator of false precision, because precession can be regular. A drill that precesses can create repeating spirals that look like intentional threads, and the repetition can be stable if the wobble locks into a consistent orbit. A tube that flexes can chatter, and chatter can be rhythmic rather than random. Chatter can produce evenly spaced ridges, because vibration can lock into a frequency set by speed and pressure, leaving a pattern that resembles deliberate machining. These are not excuses, they are mechanisms, and mechanisms are testable. Engineering is full of patterns created by unintended oscillation, and stone preserves them well because it does not spring back or self-heal. Now we place the drill holes back into the broader monument story because isolated mysteries can distort the whole picture. Holes are part of a system that includes sawing, pounding, grinding, and fitting, and the system must be coherent across an entire site. If drilling was used, it likely served specific tasks like dowel holes, relief cuts, and extraction aids, where a circular void solves a practical problem. It may not have been the primary shaping method, because flat faces and long cuts are often more efficiently made by sawing and grinding. A culture can reserve drilling for high-value operations where precision reduces risk. That choice would concentrate the best holes in the most important locations, where alignment and fastening matter more than speed. We also ask what the builders would optimize, because builders optimize what hurts most when it fails. They would optimize reliability, not spectacle, because a broken tube wastes time and risks cracking the stone, and a cracked block can ruin weeks of labor. They would also optimize repeatability through jigs and guides, which are ancient in concept and simple in materials. A simple guide frame can keep a drill vertical and reduce wandering without any advanced machine, and it can be rebuilt as it wears. So we do not need to imagine a hidden factory to imagine controlled drilling. We need to imagine disciplined process, stable fixtures, and abundant abrasive, plus the social organization to keep specialists supplied and consistent. Still, some examples remain hard to dismiss emotionally, and the camera knows it. When grooves look uniform and deep, the mind jumps to power tools, because modern experience teaches us to associate clean spirals with motors. That jump is the psychological core of the drill core mystery, and it is why the debate stays hot. The marks resemble modern machining language, so we assume modern machining grammar, even when the underlying physics could be older and simpler. Our job is to translate the marks into physical causes, without letting the first impression dictate the conclusion. We treat each claim as a hypothesis, and ask what it predicts in the surrounding evidence, because real technologies leave ecosystems of traces. If a high-speed drill existed, it would likely leave consistent heat effects, consistent tool wear patterns, and consistent geometry across many holes. It would also imply infrastructure, power transmission, durable bearings, and hardened components that should appear as artifacts, fragments, or unmistakable workshop debris. If slurry drilling dominated, it would leave more variability, more taper, and more dependence on grit availability, especially where crews worked quickly. It would also leave abrasive residues in some contexts, and it would leave worn tubes that must be replaced and discarded. We also ask what is missing from the record, because missing evidence is not neutral. Advanced drilling would require power transmission, durable bearings, and hardened components that should leave traces, and traces tend to accumulate when a method is used widely. Absence is not proof, but it is a weight on the scale and it must be acknowledged. A technology that reshapes a civilization usually leaves more than a few ambiguous grooves, because it changes supply chains, workshops, and the kinds of waste people throw away. So we end this chapter with a disciplined tension, not a neat verdict. The holes are real, the cores are real, and the striations deserve careful measurement, because granite can preserve a moment of work for millennia. Some experimental archaeology supports plausibility, while other claims remain unverified or overstated, and the gap matters. The debate persists because the best examples are not yet fully contextualized, and because our eyes are drawn to the most dramatic specimens. The central question stays intact, and it is as much about us as it is about them. Do these precise traces prove lost advanced engineering, or do they reveal underestimated human ingenuity and time, invested with a patience we rarely practice today? Drilling is a close-up mystery because it compresses the entire argument into a few centimeters of stone. It forces us to choose between impressions and mechanics, and it reminds us that looks like is not the same as is. Now we widen the lens because even perfect drilling would be only part of the story. The largest question is not how a hole was made, but how the stone was moved, staged, and set with intent. Next, we leave the drill marks and face the heaviest problem directly, where physics becomes landscape scale. We follow the engineering from the microscopic groove to the massive block, then to the act of setting it in place. The drill core debate pulled us into millimeters of evidence, carved into stubborn granite. Now we widen the lens because even perfect cutting means nothing without transport, lift, and placement. A stone can be flawless in the quarry, yet fail the moment it meets a rut, a slope, or a careless turn. Megalithic building is not one miracle repeated, it is thousands of controlled actions synchronized. The real question is not whether a block can be shaped, but whether it can be delivered intact, then set exactly. Precision is not a single act of genius. It is a chain of decisions that refuses to break. Start at the quarry, because the quarry is where engineering meets geology and risk. Extraction is not only breaking stone, it is choosing where the stone wants to break. The best quarry is not merely rich in rock, it is readable. Its fractures, grain, and bedding planes speak a language crews learn to hear. Stone is not uniform, even when it looks uniform from a distance. Granite, limestone, sandstone, and basalt each fail differently, because their crystals, pores, and microcracks distribute stress in distinct ways. A block is born from that hidden structure, and the quarryman's job is to exploit it without awakening it. In softer stone, workers can cut channels, undercut faces, and separate blocks with wedges. In harder stone, they can pound trenches, exploit joints, and force controlled fractures to follow a plan. The method changes, but the goal stays constant. Make the crack travel where you want, not where it prefers. Wedging is slow force made reliable, because it turns swelling wood or driven metal into pressure. A line of wedges can open a crack evenly, if the rock is read correctly. The physics is simple in principle. Pressure concentrates at the wedge tips, then propagates a fracture along the weakest path. Wooden wedges add a quiet advantage because water does the work after the hammer stops. As the fibres swell, they push outward with steady force, and that steadiness reduces sudden shock. In a world without hydraulic jacks, swelling wood becomes a kind of patient machine. Metal wedges, when available, trade patience for immediacy. They can be driven in sequence, moving the fracture forward like a zipper that never fully closes. But metal also transmits sharper impacts, and sharp impacts can send cracks wandering into the future face. Pounding is the other language, especially where the stone resists clean cutting. Dolerite pounders can bruise a trench, deepen it, and guide a split by exhausting the surface. Each blow creates microfractures, and those microfractures accumulate until the rock begins to behave as if it has a seam. To the eye, pounding looks crude, even wasteful, yet it is often a controlled abrasion. The trench becomes a boundary condition, a weakened corridor that invites the main fracture to follow. When the final split comes, it is not sudden magic. It is stored damage reaching a threshold. Controlled fracturing is never perfectly controlled, which is why quarrying includes sacrifice. Unfinished blocks and abandoned cuts are not mysteries, they are the cost of pushing size. A crack that runs offline can ruin weeks of labour, and the quarry floor keeps those lessons in stone. There is also the problem of internal flaws, which no surface inspection can fully reveal. A block may ring solid under a hammer, yet hide a vein, a pocket, or a healed fracture that opens under stress. Ancient crews learned to listen for tone changes because sound is a crude but useful diagnostic. Then comes dressing, and the first major logistical choice appears. Do you shape a block at the quarry, or do you move it rough and finish at the site? That decision is not just about craftsmanship, it is about risk management across a long route. Quarry dressing reduces weight and transport friction, but it increases the chance of chipping a finished edge. Site dressing increases hauling cost, but it allows final corrections against real reference lines. It also lets builders respond to surprises because the monument itself becomes the measuring instrument. This choice is not aesthetic, it is arithmetic. Every kilogram removed early saves energy across every meter of travel, even a small reduction compounds, because frictional force scales with normal force, and normal force scales with weight. Extraction also includes standardization, even when blocks look irregular. If crews can repeat typical sizes, typical lifting points, and typical sled geometry, the whole system becomes predictable. Predictability is safety, because it allows planning of rope strength, crew numbers, and ramp width. Standardization can be visible as templates and gauges, or invisible as habit. A crew that knows the usual block height can pre-build cribbing stacks, pre-cut chocks, and pre-twist ropes to the right thickness. In that sense, the quarry is also a factory, producing not only stone but routine. From quarry to monument, the problem becomes friction, not romance. A multi-ton block does not need mystery to resist motion. It needs only a rough surface and dry sand. The resisting force is measurable, and it can be manipulated with simple interventions. Sledges are the simplest transport frame because they spread load and protect edges. A sledge turns a block into a manageable package that can be dragged without direct abrasion. Its runners also create a consistent contact geometry, which makes friction more predictable from day to day. The underside of a sledge is an engineering surface, not an afterthought. A smoother runner reduces ploughing, while a slightly curved front can ride over small obstacles instead of biting into them. Even the way the wood grain runs can matter, because splitting a runner mid-haul is a disaster. Prepared tracks change the game because they control contact conditions. A levelled path with compacted fill reduces sinkage, which is often more costly than sliding friction. When a sledge sinks, the crew is no longer just sliding a load, they are pushing it uphill out of its own trench. Track preparation can mean different things in different landscapes. In some places it is packed earth, in others it is laid timbers, stone paving, or a bed of compacted gravel. The visual is unglamorous, shovels, baskets, tamping, but it is the difference between steady progress and repeated stalls. Lubrication is not a modern trick, it is a basic response to heat and resistance. Water can reduce friction in sand by changing how grains pack and shear. Wet sand can behave like a denser, more coherent medium, lowering the tendency of grains to pile up in front of the runners. There is a narrow window though, because too much water can create suction and drag. The goal is not mud, it is controlled moisture that changes grain behaviour without turning the track into a trap. That balance would have been learned empirically, with eyes on the runner and hands on the rope. Oils and animal fats can also reduce friction, but they bring supply problems and contamination. Water is cheap, abundant, and easy to apply in controlled amounts. It can be carried in jars, poured in intervals, and replenished along the route with minimal planning. The famous debate about rollers versus sledges is really a debate about terrain and control. Rollers can reduce sliding losses, but they introduce steering problems and constant resetting. They also demand a steady supply of straight, strong timbers, which is not trivial in every environment. Rollers also concentrate load on small contact lines, which can crush soil and stall progress. On soft ground, a roller can become a sinker, not a helper. When a roller digs in, the crew must lift the load to free it, and lifting is always harder than pulling. Sledges keep more contact area, and that can be an advantage when the ground is prepared. Sliding friction is high, but it is stable and predictable when the path is managed. Predictable resistance allows rhythm, and rhythm allows endurance over long distances. Either way, friction dominates the energy budget, and friction is an engineering variable. It can be reduced by smoothing, wetting, levelling, and distributing load across wider surfaces. The miracle is not that stones moved, but that the variables were disciplined enough to stay within safe limits. Ropes are not just ropes, they are force distribution networks. Multiple lines allow teams to share load, correct drift, and keep a block aligned with the track. Rope also stores elastic energy, which can be helpful in smoothing pull cycles, yet dangerous if it snaps. Fibre choice matters because strength, stretch, and abrasion resistance vary widely. Plant fibres can be twisted into thick cables, and their performance depends on humidity, wear, and knot quality. A rope is a consumable technology, and its maintenance is part of the engineering budget. Hauling is also a rhythm problem, not only a strength problem. If pull cycles are synchronized, peak forces drop, and the system avoids shock loads that break gear. A steady pull keeps the sledge just above the threshold of motion, where friction is lower than the initial breakaway. Signaling becomes a hidden technology, because timing is safety and efficiency. A caller, a drum, or a chant can coordinate hundreds of bodies into one steady motor. The sound carries farther than hand signals, and it cuts through dust, glare, and the confusion of a crowded route. Teams must also manage the block's tendency to yaw and twist under uneven pull. Side ropes, guide poles, and chocks can keep the sledge from walking off its path. A small drift at the front becomes a large misalignment at the back, and misalignment is how edges meet stone and lose. Transport includes staging because the route is rarely continuous. Blocks must be parked, turned, and sometimes lowered or raised across changes in grade. Staging areas become temporary yards, where crews can rest, inspect gear, and reset the geometry for the next segment. This is where incremental positioning becomes the core method. A block can move a meter at a time, then be secured, checked, and prepared for the next push. The securing matters because a stopped block is a potential runaway block the moment the ground shifts. Chocks, wedges, and anchor lines turn motion into controlled pauses. They also allow micro-adjustments because a sledge can be inched sideways by alternating tension on guide ropes. The visual is methodical, small moves, constant checks, yet it is exactly how large systems stay safe. When the route meets an incline, ramps enter the story, and ramps are not one design. A ramp is a compromise between distance, slope, material, and control. It is also a compromise between what is easy to build and what is easy to use. Straight ramps are conceptually simple, and they allow direct hauling with minimal turning. Their cost is volume, because a gentle slope requires enormous fill and constant maintenance. Every rainstorm, every footstep, and every passing sledge tries to undo the ramp's smoothness. A ramp is not just piled earth, because earth flows under load. Builders need retaining edges, compacted layers, and periodic resurfacing to keep the slope consistent. If the surface corrugates, the sledge begins to bounce, and bouncing turns weight into repeated impacts. Steeper ramps reduce fill, but they increase required force and risk of runaway. The steeper the ramp, the more braking and anchoring become central engineering tasks. Braking can mean drag ropes behind the sledge, ground anchors, or teams stationed as living brakes. A steep ramp also changes the consequences of failure. A snapped rope on level ground is a setback, but on a slope it can be a catastrophe. That is why redundancy matters. Extra lines, backup anchors, and procedures that assume something will eventually break. Zigzag ramps solve the fill problem by folding the path back and forth. They reduce ramp mass, but they introduce turns that complicate steering and edge protection. Each switchback is a moment when forward motion must become lateral control, and lateral control is always more delicate. Turns also create new friction losses, because the sledge must be redirected under load. A turn is a lateral force event, and lateral forces break ropes and chip corners. The outer runner wants to travel farther than the inner runner, and that mismatch must be managed by careful pacing. Spiral ramps wrap around a structure and keep the path close to the work. They can hide the ramp footprint, but they limit visibility and constrain turning radius. In a tight spiral, the crew cannot always see the front, so signaling becomes even more critical. Spiral ramps also complicate measurement, because the working face becomes partially blocked. If alignment must be checked constantly, access matters as much as slope. A blocked line of sight can turn a simple correction into a slow, risky repositioning. Counterweight concepts appear wherever gravity can be recruited as a worker. A descending mass can help raise an ascending mass, if the system is balanced and guided. The idea is ancient in principle, because it is the same logic as a well bucket and a pulley. Counterweights solve peak force demands, but they introduce control demands. A counterweight system must be braked, anchored, and protected against oscillation and runaway. If the descending mass accelerates, it can jerk the rope, and that jerk can shatter a fitting or tip a load. In practice, counterweights also require space and clear routing. The path of the descending load must be unobstructed, and the anchor points must be strong enough to hold repeated cycles. That means carpentry, stonework, and inspection, more hidden labour supporting visible motion. Lifting is not only about height, it is about controlled height. A block must rise without swinging because swing turns weight into impact. Even a small swing at the end of a lift can translate into a corner strike that ruins a finished face. Levers are the oldest lifting machines, and they scale surprisingly well with cribbing. A lever lifts a corner, then cribbing holds the gain, then the lever repeats. The lever's power comes from distance, because a long arm converts human force into a larger moment at the fulcrum. The fulcrum itself is a critical detail because it must not crush or slip. A stone pivot can crack, and a wooden pivot can deform, so builders choose materials based on load and repetition. The visual is intimate, hands, poles, wedges, yet the forces are enormous. Cribbing is incremental engineering made visible. Timber or stone stacks create temporary platforms that can be raised step by step, with stability checked at each stage. Each layer is a decision about bearing area, because a narrow stack can punch into the ground and lean. This is how slow becomes exact, because each increment is small enough to measure. A millimetre correction is possible when the load is supported and motion is limited. Large lifts are broken into many small lifts, and each small lift is an opportunity to inspect for cracks and drift. Shims are not a sign of sloppy work, they are a sign of controlled seating. Thin stone or metal pieces can distribute load and eliminate rocking without crushing edges. They also allow the final plane to be tuned, which matters when blocks must meet with tight joints. Placement begins before the block reaches its final position, because reference lines must exist. Plumb lines, stretched chords, and leveling basins turn space into a grid of decisions. These tools look simple, but they translate gravity into geometry, and geometry into repeatable checks. The block is then brought into the grid, and the grid becomes the judge. If the block is high on one corner, the correction is not guessed, it is tested. A small lift, a thin shim, a lever nudge, then the line is checked again. Iterative checking is the real engine of precision, because it converts labour into convergence. Each cycle reduces error, and the last cycles are the most expensive. The closer you get to perfect contact, the more time each improvement costs, because the remaining errors are subtle. A block can be nudged with levers, slid on thin bedding, and rechecked repeatedly. The motion is small, but the result can be exact when the reference is trusted. In the final stages, even dust and grit become enemies, because they can hold a corner high by fractions. Load distribution matters at the final seat, because stone fails at points. A high spot can concentrate stress, crack a corner, and ruin the visible face. Stress concentration is a quiet killer, because it can look stable at first, then fracture later under settling or vibration. So builders can dress contact surfaces, not for beauty, but for bearing. A hidden plane can be refined enough to spread compression and prevent long-term settling. The audience sees the outer face, but the monument's longevity often depends on invisible surfaces meeting correctly. There is also the matter of thermal expansion and weathering, which act slowly but persistently. Daily temperature cycles can open microgaps, and water infiltration can widen them over seasons. A well-seated block resists those processes because it leaves fewer pathways for water and stress. The workforce is the machine that makes all of this plausible at scale. Thousands of workers do not automatically produce precision unless their actions are standardized. Without shared procedures, more people can create more chaos, not more progress. Organization means roles, because roles reduce confusion and waste. Some crews quarry, some dress, some haul, some build ramps, some measure, and some inspect. Specialized roles also preserve skill, because repeated tasks create expertise, and expertise reduces error. Quality control is not a modern invention, it is a survival requirement. If a block is out of tolerance, it can jam a sequence and waste weeks of coordinated effort. The cost is not only the stone, but the stalled ramp, the idle crews, and the disrupted supply rhythm. Standardization can be simple, like repeating sledge designs and rope lengths. It can also be conceptual, like repeating measurement routines at every stage of movement. When procedures are consistent, mistakes become easier to spot, because deviations stand out against the norm. Logistics includes food, water, tools, and replacement parts, which are engineering inputs. A hauling crew that pauses for shortages loses more than time, it loses rhythm. Muscles cool, morale drops, and the next restart demands higher peak force, which strains ropes and joints. When we say the ancients moved mountains, we are describing a managed supply chain. The hidden technology is scheduling, inventory, and the discipline to repeat methods without improvising failures. It is also record-keeping in some form, marks, tallies, or overseers who track progress and consumption. This returns us to the central question, now expressed in pure mechanics. Do these monuments prove lost advanced engineering, or do they reveal underestimated human ingenuity scaled by time and organization? If the methods are incremental and repeatable, then the real marvel is endurance guided by measurement. The scale is political, because huge stones are not only structural choices, they are theatre because mass reads as authority and permanence reads as divine approval. A visitor does not need to understand friction coefficients to feel what a monolith implies about command. A megalith declares that a state can command labour, control land, and tame stone. It turns engineering into ideology, then sets that ideology into the ground. The monument becomes a public equation where resources and coordination are translated into a single, undeniable object. Durability is also a message, because stone outlives rulers and rewrites memory. A monument that resists weather and theft becomes a long argument for legitimacy. Even damage can serve the message, because survival through earthquakes and invasions suggests a kind of sanctioned permanence. Sacred permanence changes the cost calculus, because sacred work justifies extreme effort. When the goal is eternity, slow methods stop looking inefficient. The question becomes not how fast it was built, but how confidently it was intended to last. So the question is not why they did not choose smaller stones, but why they chose difficulty. Difficulty itself becomes proof of power, and proof of power becomes the point. The harder the task, the more it advertises coordination, an empire written in mass and alignment. Egypt is one pillar of the story, and its logistics can be modelled in steps and forces. We can imagine the quarry face, the sled track, the ramp, and the final bedding plane, each one demanding its own discipline. In that sequence, the extraordinary is assembled from ordinary actions repeated without surrender. But similar stone puzzles appear far away, where the material and style change. We turn toward Peru, where walls behave like living geology, and joints refuse simple explanations. The transport problem remains, but the fitting problem becomes stranger, and the debate sharpens again. The next chapter follows that shift, from hauling and lifting to interlocking stone that seems to anticipate earthquakes. We keep the same method, because ore is not evidence, and evidence still begins with measurement. And as we look at those tight joints, we have to ask, what did they measure, and how often did they check it? Some stones do not just rest on gravity, because in the Andes they behave like locked mechanisms. They sit with a deliberate stillness, yet that stillness is earned through contact, weight, and geometry. We arrive in Cusco, where walls run through the city like a surviving skeleton, threading past doorways and narrow streets. Blocks meet without mortar, yet the seams look sealed by intention, as if the air itself cannot find a path through. The joints bend, kink, and change angle, then return to silence, and the eye keeps searching for the trick. This chapter tests a claim that sounds like myth, but lives in measurable behaviour. Polygonal masonry has endured repeated earthquakes that shattered later buildings around it, leaving clean contrasts between survival and collapse. If the fit is real, then the method must be real, and the method must also be repeatable. The central question returns in a new language, shaped by stone and seismic risk. Do these walls prove lost advanced engineering, or do they reveal underestimated human ingenuity, time, and technique, applied with relentless discipline? If the answer is craft, then the craft had to scale into a civic system. We begin with the obvious problem because the eye cannot ignore it for long. Many stones have 6, 8, even 12 sides, and each side meets a different neighbour with a different orientation. Faces are not simple rectangles that can be squared and stacked, because they are irregular polygons that still converge into stable planes. In Cusco, the famous walls are not isolated showpieces staged for tourists and photographs. They form long runs where the same precision repeats across many blocks, including corners and slight changes in grade. That repetition matters, because a one-off masterpiece can be explained by obsession, while a cityscape implies process, training, and inspection. The joints look impossible to modernise for a specific reason that is easy to state. Modern masonry expects standard units, flat beds, and mortar that forgives small errors, then hides them behind plaster. Here, the forgiveness is removed, and the error budget is pushed into near zero, because stone touches stone directly. We also notice something subtler as the camera lingers along the seams. Many joints are not only tight, they're interdependent. One stone's outline seems to anticipate the next stone's angles. The wall reads like a solved puzzle, except the puzzle is three-dimensional and heavy. We move uphill to Sacsayhuaman, where scale amplifies every question and every assumption. Massive stones sit in zigzag terraces, and each block is shaped to meet multiple neighbours without a simple repeating pattern. A single stone can carry several joint planes, each with its own angle and curvature, and the human body looks small beside it. The terraces do not merely stack, they articulate, because the zigzag layout changes how forces arrive. Even before we talk about earthquakes, the geometry suggests an awareness of lateral loads and the need to avoid long, straight weaknesses. The light rakes across the stone faces, revealing shallow undulations that catch shadow-like topography. At Ollantaytambo, the story becomes more technical than romantic, and the site offers clues in plain view. Blocks are large, faces are dressed, and the site shows both finished and unfinished work, as if the construction sequence paused mid-sentence. Unfinished stones are crucial because they can reveal steps and decisions rather than only final perfection. Here, tool marks and partially prepared faces become evidence, not decoration. Some surfaces look roughly pecked, then partially ground, then left waiting for a final pass that never came. The quarry and the built wall feel connected, like two halves of the same workflow. Across these sites, two features keep repeating, and they repeat too consistently to dismiss. First, the joints are complex and non-repeating, with angles that vary from course to course, and even within a single course. Second, the blocks are seated in ways that resist rocking, sliding, and progressive failure, which is exactly what earthquakes try to induce. Now we shift from appearance to mechanics, because earthquakes do not care about beauty or myth. Seismic motion attacks structures by accelerating their mass, then forcing that mass to find new paths through inertia. Walls fail when stress concentrates, cracks propagate, and blocks lose stable contact, often in a rapid cascade. In simple terms, the ground moves, and the building tries to stay where it was. That mismatch produces shear forces, bending, and repeated cycles of loading and unloading that fatigue weak links. The question is not whether stone is strong, but whether the assembly can manage motion without coming apart. Polygonal masonry changes how stress travels through stone, and it does so through geometry rather than glue. Instead of long, straight joints that act like pre-cut fault lines, it creates a network of short, angled interfaces that interrupt continuity. The stress paths become distributed, and the wall avoids a single dominant fracture plane that can run unchecked. Rectangular blockwork can be strong in compression, yet it has a predictable weakness in seismic zones. Repeating horizontal beds and vertical joints create continuous lines where sliding can begin, especially when friction is reduced by dust or vibration. Once sliding begins, the wall can unzip along its own geometry, course by course. Polygonal joints interrupt that unzipping because motion cannot stay simple for very long. Variable joint angles force any sliding motion to climb, rotate, or jam, which costs energy and slows the failure process. The wall turns lateral shaking into friction, minor rotation, and controlled micro-movement, rather than a clean break. That micro-movement is not a flaw, and it is not evidence of sloppy construction. It is a form of energy dissipation, like a mechanical joint that yields slightly instead of snapping under a sudden load. The wall can breathe, then settle back into contact when the shaking ends, because gravity reasserts itself. Interlocking faces are the first part of that behaviour, and the camera can almost trace the lock. When a joint is not a straight line, the neighbour blocks resist translation through geometry alone, even before friction is considered. A block that tries to move must also lift or rotate, and gravity punishes both with immediate resistance. Variable joint angles are the second part, and their irregularity is a structural choice. If every joint angle repeated, the wall would develop a repeating failure mode, like perforations that guide a tear. Non-repeating joints prevent a single crack from finding an easy highway across the structure, so fractures must turn and lose energy. Low centre of mass is the third part, and it is often overlooked because it looks like common sense. Many polygonal walls use large blocks at the base, then smaller stones above, which is a form of mass grading. That grading lowers the centre of mass and reduces overturning moments during shaking, especially when the ground accelerates sideways. There's also the question of contact quality, because friction depends on normal force and real contact area. Tight joints increase the effective contact, which increases frictional resistance to sliding, even when surfaces are not perfectly flat. Even without mortar, the interface can behave like a high-friction clamp, because weight presses the stones together. At the microscopic level, stone surfaces touch at asperities, tiny high points that interlock and crush slightly under load. As those asperities bed in, contact can become more stable, and the wall can become more resistant over time. The effect is not magic, it is tribology, the science of friction and wear, expressed in architecture. We do not romanticize perfection, because not every joint is perfect and not every stone is untouched. Some seams are face-tight but relieved behind, and some stones show later repairs, resets, or edge damage from centuries of weathering. The point is not that every gap is zero, but that the system is engineered to survive shaking as a whole. This is where the chapter's tension sharpens into a practical question that refuses to go away. How do you shape irregular stones to mate perfectly without mortar? And how do you do it repeatedly across an entire city? If the answer is simple tools, then the process must be exceptionally controlled. We start with the simplest plausible tool chain, because plausibility must survive contact with geology. Pecking with hammerstones can remove material in controlled increments, especially when the worker understands how the rock fractures. Grinding with abrasive sand can flatten high spots and refine contact surfaces, turning roughness into fit. Pecking is slow, but it is predictable across many rock types and predictable work scales. Each strike creates a small conchoidal fracture or crush zone, then the surface is leveled by repeated impacts that gradually lower high areas. When followed by grinding, the surface can approach a controlled plane, or a controlled curve, depending on intent. Grinding is not a single technique, it is a family of techniques that can be tuned by grit size and pressure. A stone can be rubbed against stone with sand and water as the cutting medium, and the slurry carries away fine particles. The abrasive does the work, and the hand supplies pressure and repetition minute after minute. We then consider template transfer, because repetition implies measurement even when numbers are not written down. A builder can create a reference profile in wood, fibre, or thin stone, then transfer that profile to a target block by scribing or marking. The template does not need to be perfect if the fitting stage corrects the last errors through contact. Marking and subtractive fitting is the core hypothesis for many researchers, and it matches how craftspeople solve complex joins today. Place the new stone against its neighbours, identify high spots, remove those spots, and repeat until the stone settles deeper. The process is iterative convergence, where each cycle reduces error and the wall itself becomes the gauge. This method has a hidden logic that matches what we see along Cusco's long runs. Complex joints can be achieved without calculating angles in advance, because the neighbour stones become the guide surfaces. The wall itself becomes the measuring instrument, and the builder's job is to remove what does not belong. But iterative fitting raises its own cost, and the cost is physical before it is mathematical. Each cycle requires lifting and repositioning heavy stones, which demands staging, levers, rollers, and coordinated crews who can move as one. The earlier chapter on transport returns here as a necessary foundation, not a separate topic, because fitting is also moving. Trial stones may be the missing link between craft and scale, especially when the final blocks are massive. A smaller sacrificial stone can be shaped first to test a joint geometry, then used to guide the final block's contact planes. If the trial stone fits, the final stone can be brought closer to correct before the last heavy placements, reducing risk and time. We also consider the possibility of intermediate shims and temporary spaces, because edges are vulnerable during testing. A stone can be seated with controlled gaps, then adjusted as contact points are refined, protecting corners from accidental chipping. Spacers can guard the joint during repeated lifts, then be removed for final seating when the fit is ready. The wall's visible face can mislead, because the face is not always the primary bearing surface. Builders can prioritize hidden contact planes that control stability, then dress the visible face last to unify the look. That choice would explain why some faces look refined while other surfaces remain rough, because the structure is decided before the finish. Now we bring geology into the argument, because stone type sets the feasible technique and the pace. In Peru, builders worked with andesite, limestone and other local stones with variable hardness and fracture behaviour, often within the same region. A method that works on limestone may fail or slow dramatically on tougher volcanic rock, so the craft must adapt. Andesite can be hard and fine-grained, yet it can also be workable under pecking and abrasion when the worker reads its response. Limestone can be softer and more predictable, but it can also contain bedding planes that split unexpectedly under stress. Variability forces adaptive craft, not a single universal recipe, and that adaptability is itself a kind of engineering. Rock behaviour also affects edge survival, which matters in polygonal joints where corners multiply. A brittle stone chips easily at corners during test fitting, which increases waste and time and can ruin a nearly finished join. A tougher stone tolerates repeated handling, which makes iterative refinement more practical, especially when a crew must lift the same block again and again. This is why claims of a single secret technique tend to collapse under material diversity. A city built across different quarries would require flexible methods that respond to each block's grain, inclusions, and hidden weaknesses. Engineering here is not only geometry, it is reading stone, then choosing the right sequence of blows. We address the folklore directly because it thrives where methods are hard to imagine at full scale. Stories of softening stone appear in many retellings, often framed as lost plant chemistry or forgotten alchemy that turns rock to clay. The problem is that these stories rarely produce testable residues, tools, or repeatable demonstrations that can be checked against the surfaces. We separate myth from method by asking what would be measurable on surviving joints. Softened stone should show altered mineral structure, chemical signatures, or transitional textures at the joint surfaces, like resolidified flow or unusual recrystallization. The surviving surfaces instead look like worked stone, with pecking, abrasion, and dressing consistent with known mechanics and known wear patterns. That does not make the work simple, and it does not remove the mystery of labour and coordination. It reframes the mystery as process control, training, and time allocation, which are harder to dramatise but easier to test. The forbidden element may be patience, not technology, and patience can be organised into institutions. We return to why polygonal beats rectangular in seismic zones, because the advantage is structural, not aesthetic. Non-repeating joints disrupt crack propagation, forcing fractures to turn, branch, and lose energy with each change of direction. Rectangular grids invite straight cracks that grow fast under cyclic loading, because the geometry cooperates with the damage. Stress concentration is also different in polygonal walls, and the difference matters at edges. Multiple joint directions spread load across more contact faces, reducing peak stress at any single corner, especially when shaking changes direction mid-event. When motion begins, the wall has more ways to redistribute force without catastrophic separation, because it has more pathways for load. There is an additional advantage that looks like artistry, but behaves like engineering under compression. Slightly convex faces and subtle joint curvature can create self-locking contact, where weight encourages seating rather than separation. As the stones bear down, they tighten, increasing friction and stability, and the wall becomes more unified under its own mass. We acknowledge the counterpoint, because skepticism is part of the method and part of honest narration. Not every polygonal wall is equally precise, and not every earthquake spared every structure, even within the same valley. Survival can also reflect location, foundation conditions, drainage, and later rebuilding choices, which complicates simple comparisons. So we look for patterns that resist cherry-picking, because patterns are where engineering reveals itself. Where polygonal walls meet later colonial masonry, the later work often fails first, cracking along mortar lines or separating at corners. The contrast suggests a systematic difference in seismic performance, not just a lucky accident, and the camera can show the scar. We also look for evidence of workflow in the stones themselves, because workflow leaves physical traces. Some blocks show boss-like protrusions that can serve as handling points during fitting, then remain as a signature of the process. Some surfaces show partial dressing that implies a sequence from rough placement to final refinement, like a project pause between stages. The question of measurement returns, because tight joints require inspection at both the local and global scale. Builders could use straight edges, plumb lines, and sighting along courses to control global alignment, keeping walls true over long distances. For local fit, they could use soot, pigment, or clay transfer to reveal high spots during test seating, turning contact into visible information. Pigment transfer is a simple idea with powerful consequences because it makes the invisible visible. Coat one surface, press the stone into place, and the contact points mark themselves as smears and patches. Remove the stone, cut the marked highs, then repeat until contact spreads evenly and the joint begins to seal. This method explains how irregular stones can converge into near-sealed joints without mystical shortcuts. It also explains why the work is slow, because each improvement demands another lift, another check, and another careful removal. The wall becomes a record of repeated checking, not a single decisive cut, and the record is still readable. We tie this back to the earlier drill core debate, because the same logic applies across the film. Extraordinary appearance does not automatically imply extraordinary machines, because humans can achieve extreme precision through controlled iteration. It can also imply disciplined repetition, where small errors are hunted down across many cycles until the remaining error is too small to see. Yet the emotional force remains, because the joints still look like they were poured into place, like stone that learned to flow. Modern builders rarely attempt this style because it is labour-intensive and hard to schedule, and it resists modular planning. Our era optimizes for speed and standardization, which makes this older optimization feel alien, almost confrontational. So we ask what the builders were optimizing for, and the question changes the mood of the scene. In a seismic landscape, durability is not optional, and repair is expensive in time, labour, and political stability. A wall that can move and reseat after shaking is a long-term investment, even if it costs more up front and it pays back across generations. This is where the chapter's awe becomes a technical conclusion that still feels like wonder. Polygonal masonry is a form of earthquake science expressed in stone geometry, built before modern seismology named the forces. It is not anti-physics, it is applied physics without equations on paper, and it is carried in hands rather than textbooks. We end with the unresolved edge, because the film's central question must stay alive to remain honest. Even if the method is pecking, grinding, pigment transfer, and iterative fitting, the scale still demands organisation and expertise, not improvisation. The walls do not require a hidden machine, but they do require a culture that treats measurement and craft as sacred, and that can sustain it. Now the narrative widens again, because Peru is not alone, and the map begins to feel smaller. Across the Mediterranean, megaliths raise the same questions in different stone and different styles, yet with familiar obsessions about fit and mass. When distant cultures converge on similar solutions, we have to ask whether the convergence is coincidence, necessity, or shared engineering logic. Next, we follow that convergence westward, where massive blocks and tight joints appear again, and the camera finds new coastlines. The mystery changes shape, but the method stays the same, and the questions keep their sharpness. All points to where measurements belong, not to where conclusions should hide. Some stones do not just sit in place. Around the Mediterranean, they sit like decisions made permanent, heavy, public, and stubbornly uninterested in our doubts. We carry the central question into a new theatre of evidence. Do these monuments imply lost advanced engineering, or disciplined craft scaled by time, organisation, and a ruthless understanding of physics? The Mediterranean record is not one culture and one miracle. It is many coastlines repeating the same obsession with mass, stability, and endurance, an argument written in limestone, basalt, and weathered granite. We begin with Malta, where temples rise from pale limestone and uncertainty. The islands hold some of the earliest freestanding stone architecture in Europe, and the sea around them feels like a mote of time. Secure chronologies cluster in the 4th and 3rd millennia BCE. Radiocarbon sequences, stratigraphy, and associated material layers anchor faces like Gantija, Hagar-Kim, Menajdra, and Taksien, even when individual samples demand careful calibration. Calibration is not a technical footnote, it is the difference between a bold claim and a careful one. Atmospheric carbon varies across centuries, so dates must be corrected against reference curves, an invisible adjustment that keeps the timeline honest. On camera, the temples read like sculpted voids. Curved apses open from a central axis, thresholds narrow the body, and the plan suggests controlled movement. where entering is not casual but choreographed. As the lens drifts inward, the limestone brightens, then dulls, then brightens again with each shift of light. The walls are not merely boundaries, they are surfaces that catch shadows, and the shadows make the spaces feel older than their measurements. The temples are not crude piles of rock. They are planned complexes with curved apses, aligned entrances, and carefully fitted orthostats, and their symmetry implies measurement routines that were repeated until they behaved. That symmetry is not only aesthetic, it is practical. When axes align and curves repeat, builders can reuse templates, sightlines, and pacing counts, simple checks that reduce cumulative error across a long build. Their blocks can be enormous for the material and the terrain. Even when surfaces look weathered today, the original intent was deliberate geometry, flat faces, stable seats, and edges that once met with more confidence. Maltese limestone matters because it is both cooperative and unforgiving. It can be shaped with persistent abrasion, yet it also fractures along bedding and hidden weaknesses, so every oversized block is a gamble against geology. To a builder, bedding planes are both friend and trap. They can guide a clean split when you read them correctly, yet they can also peel away under load, especially when moisture and salt work into microcracks. Archaeology gives us partial tool stories. Stone hammers, flint, and later metal appear, yet the dominant cutting agent is often abrasion, sand, grit, and repeated grinding that turns time into a tool. Abrasion is slow, but it is predictable. When a hard abrasive is trapped between a tool and a softer stone, the abrasive does the cutting, and the tool mainly supplies pressure and motion. In plain terms, the sand becomes the blade. Quartz grains bite into limestone, then fracture into sharper fragments, and the process renews itself, an unglamorous chemistry of wear that rewards persistence over force. Quarry traces sit close to many temples. Extraction scars, cut lines, and abandoned pieces show that builders staged stone near the work, reducing transport distance even when the lifting problem remained brutal. In bright sidelight, quarry faces reveal shallow channels and stepped removals. You can almost see the sequence: mark, peck, wedge, test, and then the moment a fracture runs where nobody wanted it. Unfinished blocks matter more than finished ones. They preserve the sequence of decisions, including where a cut failed or a crack ran wrong, and they show that ability often includes the ability to abandon. Abandonment is not defeat, it is quality control. Leaving a flawed block in the quarry prevents hidden weaknesses from migrating into a temple wall, where a single failure could propagate into a visible collapse. Tool marks in Maltese limestone can be read as pecking, chopping, and grinding. The marks imply repeated passes rather than a single decisive cut, and that repetition is exactly what a low-tech toolkit excels at. Even the negative evidence is informative. If a high-speed saw had been used widely, we would expect consistent kerf widths, systematic striations, and large volumes of uniform slurry. Yet the record is quieter and more irregular. Transport on Malta is a fragmented landscape problem. Short hauls over uneven ground can dominate effort more than long-distance travel, because every slope multiplies friction and every turn demands control. Local solutions appear plausible and varied. Sledges, rollers, and levered cribbing can move heavy stones when the route is prepared, and prepared can mean weeks of levelling, packing, and clearing. A prepared track is engineering in disguise. It means compacted soil, stone chocking, and deliberate gradients, and it means removing the small obstacles that become catastrophic when tons of mass start to slide. A sledge turns jagged ground into a manageable surface problem. Load spreads across runners, edges stay protected, and the crew can brake with drag ropes, because gravity is always waiting for a lapse. Rollers can work on firm ground, yet they demand constant resetting and good timber supply. On rocky terrain, rollers can jam, split, or walk sideways, and the stone does not forgive sudden shifts. Levers, in contrast, are universal. A long beam, a fulcrum, and patient cribbing can raise a block a few centimetres at a time, and those centimetres are how alignment becomes possible. Those centimetres also let builders listen and watch. If a block creaks, tilts, or begins to crush its bedding, the crew can pause, because incremental lifting turns a dangerous moment into a series of manageable checks. The famous cart ruts complicate the story without solving it. They could reflect transport, drainage, or repeated traffic, and their dates remain debated, which means they cannot be used as a single master key. What Malta does prove is planning under constraint. Small islands still produced large stones because permanence and prestige were part of the design brief, an insistence that the sacred should outlast the living. The visual impression is intimate rather than imperial. These are not mountains of stone, but chambers and corridors where a human body feels measured, and where the weight above your head becomes part of the experience. From Malta we move east and north, into late Bronze Age Greece. Here the style changes, yet the scale of stone becomes even more confrontational, and the architecture shifts from sanctuary to survival. Mycenaean citadels use Cyclopean masonry. Tyrins, Mycenae and Medea stack irregular boulders into walls that look immune to time, and their silhouettes still dominate ridgelines like warnings. Ancient writers later claimed only Cyclopes could build them. The myth is a clue to perception, because mass can feel like a violation of human limits, especially when the joints vanish into shadow. Archaeological dating is firmer than the legends. The major fortification phases cluster in the 13th century BCE, with earlier foundations and later repairs, and the sequence matches a world under pressure. That pressure has a wider horizon. The Late Bronze Age is a networked Mediterranean, with ships, trade goods and diplomacy. Yet it is also a period of disruption where fortification becomes an architectural reflex. This is a landscape of palaces, storage and administration. Clay tablets, controlled goods and hierarchical labour suggest that coordination was not accidental, and that large projects could be scheduled like campaigns. These walls are not random heaps. They are engineered systems that manage weight, impact and long-term settlement without mortar, and they do it by forcing stone to behave in compression. Thickness is the first engineering fact. Many Cyclopean walls are several meters thick, sometimes with galleries or internal corridors that reduce weight and add function, while keeping the outer face intimidating. In cross-section, the wall is a machine for stability. Outer boulders act as a shell, inner fill locks them in place, and the whole mass resists sliding by sheer friction and interlock. Batter angles are the second fact. Slight inward lean stabilizes the face by shifting the resultant load inward, reducing the chance of outward bulging when the core settles or vibrates. Load paths are the third fact. Large stones create fewer interfaces, and fewer interfaces can mean fewer weak planes under shock or siege, because every joint is a potential slip surface. Overbuilding can be rational rather than irrational. In defensive architecture, redundancy buys time, and time is the currency of survival. Time to rally, time to endure, time to outlast a season. A thick wall resists more than arrows. It resists rams, fire, undermining, and the slow damage of earthquakes and settlement. And the Mediterranean is not gentle with seismic memory. The irregular polygonal faces also have logic. Varied joints can interrupt continuous fracture lines, forcing cracks to turn and lose energy, which is a plain language way of saying the wall refuses clean failure. This is not the same as Peru's precision puzzle. Mycenaean joints are often looser, yet the system still depends on careful placement and stable bearing. Stone on stone, weight on weight. Watch the wall in raking light, and the method becomes visible. Each boulder is seated, shimmed, and tested by gravity itself, and the builder's measurement is sometimes the sound of a rock settling. We look for the evidence that connects wall to quarry. In Greece, quarry sources can be local outcrops, field boulders, and cut stone from nearby ridges, which means procurement is often a patchwork. Patchwork procurement is not a weakness, it is an adaptation. If a boulder already lies in a field, the quarrying step is reduced, and the labour shifts toward hauling, seating, and controlling the final fit. Quarry evidence is uneven because later building reuses stone. Still, extraction scars and roughouts show that blocks were shaped enough to seat safely, and that final fitting could happen at the wall face. Tool finds do not give us a missing machine. Bronze tools exist, stone tools persist, and abrasives remain the quiet workhorse for finishing, especially when metal must be conserved. Bronze is not steel, and that matters. It dulls faster on hard stone, it bends under misuse, and it rewards controlled technique, short strikes, careful angles, and frequent resharpening. If high-speed mechanized cutting had existed, it should leave an ecosystem of traces. We would expect standardized wear patterns, workshop debris, and hardened components, along with consistent geometry across many sites. Across these Mediterranean sites, that ecosystem is thin. The record instead favors dispersed craft, repeated procedures, and tools that leave ambiguous marks, which is exactly what we see in pre-industrial stonework. We widen the survey beyond Malta and Mycenae. The Mediterranean is full of megalithic statements that cluster around the same engineering pressures, even when the cultures and languages were strangers. In Sardinia, nuraghi rise as stone towers with corbelled interiors. Their stability comes from mass distribution, stepped courses, and careful stone selection, each ring leaning inward so the load closes like a fist. Inside a nuragh, the air cools and the sound changes. The corbelled dome narrows overhead, course by course, and the geometry feels less like decoration than like a controlled surrender to gravity. In the Balearics, talayots and taulas show another regional grammar. The stones are large, the forms are simple, and the intent is communal permanence, as if the island itself demanded a signature in rock. In Italy, polygonal walls at sites like Alatri and Norba provoke debate. Their tight joints invite claims of a lost technique, yet their dates and phases are contested, and the masonry may represent multiple episodes. Some walls may be Iron Age, some may incorporate earlier work, and some may be rebuilt repeatedly. Uncertainty becomes fuel for speculation when the stones look too confident, and confidence is easy to romanticize. We do not treat uncertainty as permission to invent. We treat it as a measurement problem, where better sampling, clearer stratigraphy, and transparent publication can narrow the range without myth. Chronology is the hinge between awe and explanation. If dates shift by centuries, the toolkits and social systems shift with them, and the same wall can mean different things in different centuries. For Malta, the early dates are strong enough to be uncomfortable. Monumental building appears before widespread metal, which forces us back to stone, abrasion, and organization, plus the willingness to spend labor like water. That labor has a human texture. It means crews, schedules, food supply, injury risk, and leadership. And it means that the temple is also a social machine that holds people to a shared purpose. You can imagine the logistics in the background. Someone must count hands, distribute rations, and decide when a block is good enough, because perfection is expensive and the calendar never stops. For Mycenae, the Bronze Age context is clearer. Palatial administration, labor control, and regional conflict make fortification investment comprehensible, because protection of stores and elites becomes strategic necessity. For other regional works, the secure facts vary by site. Some have datable ceramics and construction layers, while others rely on style and later texts, and style is persuasive but not always precise. Now we focus on quarry signatures, because quarries are where claims can be tested. Extraction scars show whether blocks were cut, wedged, or fractured along bedding, and they reveal how builders negotiated natural planes. A quarry is also a laboratory of failure. It shows the cost of misreading stone, when a wedge line runs off, when a seam opens, and when a promising block becomes rubble in seconds. Unfinished blocks show where ambition met material limits. A crack that wandered can explain why some stones were abandoned, even when the goal was enormous size, because a hidden flaw can erase weeks of work. Tool marks can be read, but they must be read carefully. Lighting, weathering, and later dressing can imitate machining and exaggerate regularity, especially when surfaces have been refaced across centuries. Chisel lines in soft limestone can look like saw marks. Pecking pits can merge into grooves, and abrasion can smooth them into deceptive planes, which is why close-range photogrammetry has become so valuable. Photogrammetry turns surfaces into measurable topography. Under the model, a groove has depth and profile, not just appearance, and that profile can separate a repeated hand motion from a single rigid machine pass. The correct question is not whether marks look modern. The correct question is whether the marks match a repeatable process with known tools and abrasives, and whether that process scales across an entire site. We compare finishing demands across the region. Temples often require visible faces and controlled alignments, while fortresses prioritize stability and speed under threat, and those priorities shape where precision appears. That difference changes where labor is spent. A defensive wall can accept irregular faces if the core is stable, while a temple front may demand tighter presentation, because the front is part of the ritual message. In practice, builders make selective investments. They dress what will be seen, they stabilize what must carry load, and they leave hidden surfaces rough, which is not laziness but efficiency. Transport returns as the hidden constraint linking all these sites. Mediterranean landscapes are broken by ridges, terraces, and short, steep climbs. and the sea that connects cultures also isolates building platforms. In such terrain, short-haul methods dominate. A block may travel only a few kilometers, yet those kilometers can include the hardest meters of the entire project: switchbacks, pinch points, and final approaches. Sledges remain the most controllable option on prepared tracks. They spread load, protect edges, and allow braking on slopes with drag ropes and anchors, and they can be repaired with simple materials. Capstans and windlasses offer another path. A fixed anchor and rotating drum can convert steady human force into controlled pull, especially on inclines where a surge could shatter a stone or a crew. When a capstan turns, it turns time into distance. Each rotation is small, but it is reliable, and reliability is what heavy transport demands more than raw strength. Levers and cribbing close the gap between transport and placement. Incremental lifting reduces risk, and it allows alignment checks at every stage, which matters when a misseat can concentrate stress and crack a corner. Placement is often the true climax. Moving a block is one problem, but setting it onto a stable bearing without modern cranes requires choreography, signals, and the patience to back out and try again. Even the ground beneath the block matters. A bearing surface must be level enough to avoid point loading, because point loading turns weight into fracture, and fracture turns a triumph into debris. Terrain shapes method more than ideology does. A flat plain invites long ramps, while a hillside site invites switchbacks, staging yards, and micro-movements. And those micro-movements are where most time is spent. This is where convergence begins to feel less mysterious. Different cultures face similar constraints, and constraints can produce similar solutions, because there are only so many ways to persuade stone to cooperate. Stability is one shared problem. Stone is strong in compression, weak in tension, and every builder learns to keep loads centered and interfaces seated, even when the knowledge is learned by costly mistakes. Permanence is another shared problem. A monument must survive weather, settlement, and conflict, and mass is a simple hedge against uncertainty. More weight, more inertia, fewer surprises. Prestige is the third shared problem. Large stones are political theatre, because they translate coordination into a visible fact that cannot be argued away, and they make leadership feel inevitable. Convergence does not require diffusion, though diffusion can happen. It can be enough that humans everywhere discover the same mechanical truths by trial, and then teach them through apprenticeship rather than texts. Still, the similarities raise a legitimate question. Did ideas travel with traders and sailors, or did each region reinvent the same techniques, guided by the same mathematics of friction and leverage? We keep the debate grounded in evidence. Shared motifs can suggest contact, yet stone size alone is not a motif. It is a response to physics, and physics does not care who speaks which language. When claims of hidden technology appear, we return to the drill core standard. Extraordinary tools should imply standardized outcomes and a supporting infrastructure, spare parts, workshops, and a trail of consistent byproducts. In the Mediterranean record, the infrastructure is mostly absent. What remains are quarries, hammerstones, abrasives, ramps, and the long patience of iteration. Methods that look humble until you calculate the labour. That does not erase the hardest questions. Transport of the largest blocks still strains simple models, especially where routes are steep and turning space is limited, and where a single slip could be catastrophic. Finishing also remains contested. Some faces look too regular, some joints look too deliberate, and weathering can hide the intermediate steps we need, leaving us with end states but not the full sequence. Purpose is the final contested layer. Why choose extreme stone sizes when smaller blocks could work, unless the difficulty itself was part of the message, an intentional display of commitment and control? In temples, extreme stones can signal sacred permanence. In fortresses, extreme stones can signal deterrence, because attackers read mass as futility, and futility can prevent a fight before it begins. The Mediterranean giants therefore converge on a shared logic. They are not only buildings, they are arguments made of geology and labour, arguments that say, we were here and we could organise. We end this chapter with a controlled discomfort. The monuments are extraordinary, yet the toolkits look ordinary, and the gap is where speculation breeds, especially when the stones still feel impossible. So we tighten the question for the next test. What were builders actually capable of with Bronze Age tools, abrasives, and measurement routines, when time was treated as sacred and repetition was treated as wisdom? We do not need a hidden machine to feel awe. The forbidden engineering may be the discipline to repeat small corrections until stone behaves like certainty, and until error becomes something you can manage. Next, we test the limits directly. We move from surveying giants to reconstructing capability, where experiments, tolerances, and failure rates become the evidence. Some stones look machined, and our instincts reach for hidden machines, because straight lines and clean joins feel like signatures. Chapter 7 is the reality check that keeps awe honest and keeps method in control. We begin by inventorying what is actually on the table in most Bronze Age contexts, not what we wish were there. Copper and bronze chisels and saws appear in graves, workshops, and quarry debris, often bent, blunted, and resharpened. Stone pounders, frequently dolerite or similarly tough igneous rock, show battered faces and polished handholds from long use. Wooden mallets, levers, and wedges rarely survive, yet their impressions and the logic of carpentry follow them like shadows. Flint blades and scrapers persist as a parallel technology, because sharpness can matter more than material prestige. Early iron appears later in some regions, and it changes margins without rewriting physics. Visually, the toolkit is almost disarming in its simplicity. A thin copper blade catches the sun and looks fragile beside a block of granite. A rounded dolerite pounder sits heavy and matte, its surface bruised with tiny craters. A bundle of wooden wedges looks like firewood until you imagine them driven into a seam, then soaked until they swell. The scene is not futuristic, yet it is not primitive either. It is a system. Hardness is the first trap because it sounds like a verdict. Mohs numbers describe scratch resistance, not overall cutting ability, not toughness, not edge stability, and not the full system of tool plus abrasive. A hard mineral can be brittle, and a softer metal can be stubbornly ductile, which matters when edges deform rather than shatter. Even within one rock, hardness varies because crystals, grain boundaries, and micro cracks create a landscape at the scale of sand. Copper and bronze are softer than quartz, feldspar, and many igneous stones. That mismatch is real, and it matters, but it does not end the conversation. It forces us to ask whether the metal edge was ever meant to be the tooth. In many ancient cutting systems, the metal is less a knife and more a frame, a way to deliver pressure, alignment, and motion. Stone pounders are blunt, yet they can remove hard rock reliably, and their effectiveness is measurable in scars. They do it by crushing and spalling, not by slicing, and the surface they leave is a predictable field of pits. Each impact concentrates stress, and stress finds weaknesses along crystal boundaries and tiny flaws. A pitted surface is not failure, because it is a controlled starting state. It is the roughing stage, the moment when mass is moved and shape begins. In a quarry face, that roughing has a rhythm you can almost hear. Strike, rotate, strike again, and the rock responds with a dull report and a dust that clings to skin. The worker is not carving a final plane, because the goal is to approach a line from a safe distance. The pits become a map of where the next blow should land, and the map is legible to trained eyes. Wooden tools sound like a joke until you remember wedges and leverage, which are older than metal. Dry wood swells when wet, and swelling can apply steady force for hours, even days, without fatigue. The wedge is slow power, and slow power breaks stone when impact would shatter it wrong. A crack that creeps is often better than a crack that runs wild. This is also why ancient quarrying often looks patient rather than violent. A seam is prepared, wedges are driven, water is introduced, and the rock is asked to separate on terms the worker can predict. When the split finally speaks, it is not an explosion but a long release, like a taut rope giving way. The visual drama is subtle, yet the engineering is precise. Flint is brittle, yet it is extremely sharp, and it excels on softer stones and on fine trimming. It also creates distinctive fracture and microchipping patterns that can be compared to surviving marks. A flint edge can be sharper than many modern steel edges, at least briefly, because its fracture produces a near-molecular wedge. Flint does not solve granite, but it solves many steps around granite. It can trim clay, cut rope, shape wood, and refine softer limestone that frames the harder work. Early iron enters as a late variable, not a universal key. Iron can hold a harder edge than bronze, but it still struggles against quartz-rich stone without abrasives. It also rusts. It can be inconsistent in carbon content, and it demands different forging skills than copper alloys. The narrative must not smuggle in steel performance where only early iron exists. A harder tool helps, but it does not erase the need for grit. Now we name the hidden blade that keeps returning across sites. Abrasives, quartz sand, crushed quartz, emery in the right geologies, corundum-bearing sands in rare but real deposits. These materials are not exotic inventions, because they can be gathered from riverbeds, beaches, and weathered outcrops. What is rare is not the mineral, but the insight to treat it as a cutting edge. Abrasives turn a soft tool into a cutting system, because the grit is the tooth. The metal becomes a carrier that holds grit in place and supplies pressure and motion. The cutting edge is not the copper, it is the trapped mineral. Under load, grains embed into softer metal or into a wooden or stone carrier, and their sharp corners do the work. A slurry is a simple machine made of water, grit, and repetition. Water carries grains into the contact zone, cools the interface, and removes fines that would otherwise polish and slow cutting. Slurry also renews itself as grains fracture into sharper fragments. In plain terms, the process keeps making new tiny knives, even as old ones dull. This is why the tool can be softer than the stone and still win. If the abrasive is harder than the workpiece, the abrasive does the scratching and ploughing. The tool only needs to survive long enough to keep feeding grit through the cut. That survival is not trivial, because soft metals deform, yet deformation can actually help by trapping grains. We connect this to the central question without dodging its emotional power. Do precise monuments prove lost, advanced engineering, or do they prove we underestimate abrasion, measurement, and organised labour? The answer depends on what the traces demand, not on what feels intuitive. Ore is a starting emotion, but it cannot be the final method. Sawing comes first, because straight cuts create the illusion of modernity. A copper saw blade can be toothless and still cut granite with quartz sand. The blade acts as a guide rail, and the kerf is carved by grit rolling and sliding under pressure. The motion can be push-pull by hand, or it can be assisted by weight and a steady rhythm. Imagine the scene in close-up. A thin blade rides in a growing groove, and a muddy paste squeezes out with each stroke. The sound is not a scream of metal teeth, but a gritty hiss, like sand under a boot. Over time, the groove deepens, and the blade's path becomes self-stabilizing, because the kerf constrains it. We outline the mechanics that should leave readable evidence. Abrasive sawing produces a kerf whose walls show fine, parallel striations aligned with stroke direction. The striations can vary in depth as grit size changes, and they can cross slightly if the blade rocks. The blade itself wears, so kerf width can widen over time and show slight taper. If the blade flexes, the kerf can reveal that flexibility as subtle waviness. A powered saw would tend to standardize these signatures, because speed and pressure become more uniform. A hand-driven saw tends to vary with stroke length, pressure, and grit size, especially as fatigue sets in. Variation is not a weakness, because variation is what human systems naturally produce. The question is whether the variation matches the expected physics of slurry cutting. Drilling is the next pressure point, because circles trigger industrial assumptions. Tube drilling with copper and abrasive can produce cylindrical holes and cores. The tube does not need to be harder than granite because the grit at the rim is the cutter. The tube simply defines the diameter, while the abrasive defines the bite. The visual is striking when a core survives. A stone cylinder, freed from its parent block, looks like a modern plug pulled from concrete. Yet the process can be ancient in its logic. Rotation, downward pressure, and a constant feed of abrasive slurry. In some setups, a bow drill or weighted spindle can supply rotation, while assistants keep the slurry alive. We state what wear patterns should look like in a slurry drill. Spiral or helical striations can form if rotation and feed are steady, but they should vary with interruptions and grit changes. The core should show matching grooves, and the whole wall should show consistent abrasion bands. If the drill chatters, the grooves may deepen in repeating intervals because the tool bounces under load. We return to the promise from the drill core chapter, and we tighten it into a test. Reported high feed rates and dramatic spirals must be measured across many samples, not selected photographs. Lighting can exaggerate grooves, and weathering can soften them into misleading curves. If the most extreme examples are rare, damaged, or reworked, the story changes. If they are common and consistent, the burden shifts back to our models. We also return to the ecosystem argument because it is the strongest check on fantasy. If high-speed mechanized drilling existed, it implies bearings, hardened parts, power transmission, and workshop debris. Those supporting traces should cluster where the holes cluster, because machines are not shy about leaving waste. They shed broken components, worn surfaces, and standardized byproducts. The record we actually have is uneven and often quiet. We have copper tools, stone pounders, abrasive residues, and ambiguous grooves. We do not have a widespread infrastructure of hardened components that would make a machine culture unavoidable. We also do not see universal standardization in hole geometry across regions, which is what industrial tooling tends to impose. That absence is not proof of absence, but it raises the burden of proof. A hidden machine that leaves only perfect holes and no supporting ecology is a claim that fights against how technology usually behaves. Technologies spread, standardize, and leave waste. They create supply chains, training traditions, and repair habits that echo through a site. Now we shift from cutting to measurement, because precision is enforced, not wished into existence. Metrology can be simple and still produce powerful outcomes, because geometry is generous when you check it often. A plumb line defines vertical, and it does so with gravity as an uncheatable reference. A water level defines horizontal across distance, because water seeks the same height in connected vessels. A set square defines right angles without numbers, and it can be made from wood, stone, or metal. A straight edge defines flatness by contact and light, because gaps reveal themselves when you look along the edge. Measuring cords and knotted ropes define repeatable lengths and diagonals, and they can be recalibrated against a master length. Sighting poles and aligned stakes define long axes and gradients, turning landscapes into drawn lines. These tools do not require advanced math to be effective, although practical geometry often emerges naturally from repeated building. They require repeated checking, disciplined correction, and a culture that treats small errors as unacceptable. Precision is a behavior before it is a device. The mind is part of the instrument, because attention is what keeps the line true. We connect metrology back to Peru's fitting question. What did they measure, and how often did they check it? The answer can be constant checking, because iterative fitting turns the wall into a gauge and turns contact into data. A stone is lifted, seated, rocked, and removed, and the bright spots of contact tell you where to trim next. Over many cycles, the wall becomes a three-dimensional template. We connect metrology back to Egypt's granite problem. Flatness and squareness can be approached by abrasion against reference surfaces and by repeated straight-edge checks. The process is slow, but it converges, and convergence is the point. When two surfaces are rubbed with abrasive, high spots are preferentially removed and the surfaces approach a shared plane. Now we name the multiplier that modern viewers resist: labour and time. Not as vague hand-waving, but as an engineering parameter that can be budgeted and optimized. When time is available, you can trade speed for control, and control is what precision feeds on. Slow processes can be more accurate than fast ones, because they allow correction between steps. Fast removal hides errors until they are expensive, and it can overshoot the target before you notice. Slow removal reveals errors early, when they are still cheap to remove. In stonework, the cheapest mistake is the one you catch while it is still a scratch. Abrasive work is naturally incremental, and incremental work is naturally inspectable. Each pass removes a thin layer, and each inspection can redirect the next pass. Precision emerges from feedback loops, not from single heroic cuts. The romance of the perfect strike is replaced by the discipline of the next adjustment. Optimization in ancient projects can mean something different than modern optimization. Modern systems often optimize for speed, throughput, and standardized parts, because markets reward volume. Ancient monumental systems can optimize for certainty, repeatability, and long-term stability, because the cost of failure is political and sacred. A block that does not fit is not just waste, it is delay, embarrassment, and risk. We describe how labor can be organized into accuracy. Crews can specialize in roughing, in dressing, in polishing, and in measurement, so that skill deepens rather than resets each day. Apprenticeship can standardize hand motions, because repetition trains the body as much as the mind. Foremen can enforce tolerances with simple gauges and refusal to accept bad fits. Quality control can be social pressure made visible. This is where the social machine becomes visible behind the stone machine. Food supply, scheduling, tool resharpening, grip procurement, and transport staging become part of the cutting system. engineering is not only tools, it is coordination. A quarry without logistics is just a cliff, and a workforce without rhythm is just a crowd. We address the common objection that time alone cannot explain perfection. Time does not guarantee precision, but time allows iteration, and iteration allows precision. The question becomes whether the workflow supports iteration without catastrophic rework. If a project is designed to allow small corrections, then small corrections accumulate into startling results. We outline a plausible workflow that links earlier chapters, quarry roughing by pounding and wedging, with fracture guided rather than forced, transport by sledges, levers, and staged routes, where friction is managed with water, rollers, or prepared trackways, initial seating and marking where the stone is introduced to its neighbours like a test fit, repeated lift, trim, and reseat cycles where contact points are read and corrected, final dressing and polishing where it matters, because not every hidden face needs a mirror. We keep the tension alive by naming where the limits may still be. Scaling precision across thousands of surfaces is not the same as finishing one showcase block. Consistency is harder than brilliance, because consistency requires inspection systems that do not tire. It requires record-keeping, training, and a shared definition of good enough that is stricter than comfort. Circular drilling is another limit zone. Making one straight hole is possible with patience, but making many holes with consistent diameter, roundness, and alignment is a higher bar. If a site shows systematic consistency, we must explain the control method. Was the drill guided by jigs, by templates, by repeated measurement, or by a specialized crew that did nothing else? Finishing hardness in certain stones is a third limit zone. Some rocks resist polishing and resist crisp edges because their grains tear out, especially when crystals are large or poorly bonded. A mirror-like finish on tough stone demands fine abrasives, controlled pressure, and long time, and it also demands that the finish survives weathering. If a surface is still glossy after centuries, we must ask what mineral mix and maintenance made that possible. We also acknowledge the limit of our own inference. Weathering, later repairs and reuse can erase intermediate steps, and restoration can overwrite original tool marks. A final surface can look like a single action when it was actually 100 actions. Absence of visible steps is not evidence that steps never existed. It is a reminder that stone records history unevenly. Now we tighten the chapter into a disciplined claim. Many outcomes that look impossible are possible with soft metals when abrasives are harder. Many outcomes that look modern are achievable with simple metrology when checking is relentless. The world does not need a secret motor to produce a straight line if the line is checked 1,000 times. Yet we refuse to turn this into a debunking sermon. Some specific claims still demand better sampling, better measurement, and transparent publication. The correct response to an anomaly is not belief or dismissal, it is a protocol. A protocol is how awe becomes knowledge without becoming cynicism. We propose what that protocol must include. Large sample sizes across a site, not a few famous stones, because outliers can dominate a story. Surface topography, measured, not guessed from lighting, because shadows can lie with elegance. Replication experiments that publish failure rates, not only successes, because real craft includes broken tools and ruined attempts, and careful context, because a mark without provenance is a mark without meaning. We return to the emotional hook, because the film is still about awe. Stones that lock into reality with modern-seeming precision are not less impressive when the method is simple. They can be more impressive, because simplicity means the achievement is human-scaled and repeatable. It means skill lived in hands, not hidden behind a curtain. Now we pivot to the chapter's final tension, because the evidence is not only physical, it's social. Why do some claims get labelled forbidden, while other claims get labelled settled, even when the measurements are incomplete? Why does one question get treated as curiosity and another as provocation? Forbidden can mean many things at once. It can mean a challenge to national narratives, where monuments serve as anchors for identity. It can mean a threat to professional authority, where careers are built on stable timelines and accepted methods. It can mean a market for sensationalism that rewards certainty over careful doubt. In each case, the label is less about stone and more about stakes. Interpretation becomes a battlefield when identity is attached to conclusions. Skeptics fear gullibility, and believers fear gatekeeping, and both sides can stop measuring. The stone does not care, but the audience does. The tragedy is that the monument becomes a mirror, reflecting our loyalties more than our methods. So we set the stakes for the final chapters. If the toolkit can explain more than we assumed, then the mystery shifts toward organisation, training, and quality control. If the toolkit cannot explain key patterns, then the anomaly becomes sharper and harder to ignore. Either way, the next step is not louder claims but cleaner measurements. We end with the conclusion theme stated as a challenge, not a comfort. The most forbidden engineering may not be a hidden machine. It may be a forgotten respect for disciplined craft, where time, measurement, and materials are treated as sacred. And if that respect once existed, what would it demand from us now? Next, we enter the battlefield of interpretation directly, where claims will be weighed against incentives, institutions, and the stories we want the past to tell. Some stones don't just sit in place, they seem to lock into reality with a precision that feels modern. Under raking light, edges snap into shadow like a ruler line, and faces look planed rather than fractured. If Bronze Age hands shaped them, why do surfaces whisper of machining, measurement, and methods we struggle to reproduce? The camera lingers on a seam so tight a blade can't enter, and the mind reaches for explanations with gears. By Chapter 8, the argument is no longer only about stone, it's about how people decide what counts as knowledge and who gets to say it. The fight is not merely over a wall or a block, but over the rules that let any claim stand upright. When those rules feel unfair, every measurement becomes political, and every photograph becomes a weapon. The central question stays fixed. Do precise monuments prove lost advanced engineering, or do they reveal how much we underestimate human ingenuity, time, and technique? That question sounds technical, yet it carries a hidden charge, because it asks whether the past is familiar or fundamentally alien. We start with the mainstream framework, because it is built to survive disagreement. Archaeology is not a single opinion. It is a system of constraints that tries to keep stories tied to context. It is messy on purpose, because the past is a shattered object, and reconstruction demands discipline. Peer review is the first constraint, and it is both protection and friction. In theory, it forces a claim to face hostile questions before it meets the public. Reviewers ask about sampling, calibration, and whether alternative explanations were tested, not just mentioned. Yet peer review is also human, limited by time, expertise, and the quiet bias toward what seems plausible. When a paper challenges a settled narrative, the bar can feel higher even without malice. Unconventional ideas often arrive with incomplete datasets, and incomplete datasets invite conservative decisions. That caution can look like suppression from the outside, especially when the subject already feels charged. Context is the second constraint, and it is the one the public rarely sees. An object without context is a sentence without a paragraph, and meaning collapses when provenance collapses. Context is not just where something was found, but what was beside it, above it, and sealed around it. A tool in a layer with charcoal, pottery, and plaster tells a different story than the same tool on a market table. The visuals shift to an excavation square at dawn, string lines, tags, and careful trowel strokes. Each bucket of soil is not dirt, but a page being turned, and the page can only be read once. When context is lost, the object becomes louder than it deserves to be, because nothing is left to contradict it. Stratigraphy is the third constraint, and it is brutally simple. Layers form sequences, sequences form timelines, and timelines decide which toolkits are even possible. In plain language, the ground keeps receipts, and those receipts are stacked in order. A cut through layers can be dated by what it cuts, and a fill can be dated by what it contains. Stratigraphy is not perfect, because sites are disturbed by roots, floods, and later builders. That's why archaeologists look for sealed contexts, floors, foundation trenches, and collapse layers that act like time capsules. When a block is reused, its surface may be older than the building that holds it, and that distinction matters. Replication is the fourth constraint, and it is where romance often breaks. A claim becomes stronger when independent teams can measure the same thing, using methods that survive scrutiny. Replication is not only about repeating an experiment, but about repeating a result under different hands, different instruments, and different expectations. If the effect vanishes when the lighting changes, it was never an effect. Provenance matters as much as the object, because provenance is the chain of custody for history. A perfect artifact with a broken chain can be real, yet still be unusable as evidence. Evidence is not just an impressive thing, it is an impressive thing with a documented life. This is why looting is not only theft, it is data destruction. When a piece is ripped from a layer, the layer's date, associations, and story are erased. The loss is cumulative, because one missing object can collapse a whole sequence of inference. The camera shows a scarred pit where the ground has been churned, and silence stands in for what was removed. Museums and archives become the next pressure point, because access shapes trust. When a storeroom is closed, the public reads secrecy, even when the reason is conservation or staffing. Many collections are vast, and only a fraction can be displayed under safe light and stable humidity. In storage, objects rest in drawers and crates, labelled in codes that feel like a private language. Language barriers deepen that impression. Key reports sit in specialised journals, behind paywalls, or in local publications that never reach the global debate. Some are written in technical shorthand because the intended audience already knows the site history. To a non-specialist, that opacity feels like a locked door, even when it's simply a professional dialect. Gatekeeping can be real without being a conspiracy. Limited time, limited budgets, and professional incentives can still create a wall that looks like intent. A curator may have one staff member for thousands of objects, and every handling request carries risk. When access is rationed, the rationing itself becomes a story. Now we move to the alternative theories, because they are not just entertainment, they are narratives that answer emotional needs, and emotional needs are powerful engines. They offer a clean shape to a messy world, and they turn scattered facts into a single dramatic line. Lost civilization stories promise a missing chapter that makes the world feel larger. They turn scattered anomalies into a single arc, and an arc is easier to remember than uncertainty. The visuals cut between distant sites, massive blocks, polished faces, and joints that look poured rather than placed. The implication is seductive. If these are connected, then history has a secret spine. Outsider theories promise rescue from complexity. If the builders were not local, then the puzzle feels solvable by importing a single superior method. Complexity is exhausting because it means many small solutions rather than one grand key. A stranger with a blueprint is easier to picture than generations of trained hands. Suppressed discovery stories promise drama with a villain. They explain why the viewer has not heard the evidence, and they convert ignorance into proof of cover-up. The narrative is emotionally efficient. Every missing document becomes intentional, and every closed archive becomes a confession. These ideas resonate because they protect awe. If the stones feel impossible, then a hidden technology preserves that feeling, and it prevents the anticlimax of patient craft. Awe is fragile, and people defend it the way they defend a sacred place. If the answer is abrasives, levers, and time, some hear it as nothing special happened here. They also resonate because modern life is saturated with lost trust. Institutions fail in visible ways, so people generalize that failure into every domain, including the deep past. When authorities contradict themselves on current events, it becomes easier to believe they are lying about ancient ones. The past becomes a stage where modern suspicion can perform. The internet amplifies this pattern by rewarding certainty. A careful paper has caveats. A viral claim has a punchline. Nuance is harder to share than outrage, and outrage travels farther than a graph. Media incentives shape the entire battlefield. Editors want conflict, platforms want retention, and algorithms reward the most confident voice, not the most careful measurement. The camera shows a scrolling feed, caps lock headlines, dramatic arrows, and zoomed-in circles that imply revelation. What gets clicked becomes what gets believed. This is where the debate turns toxic, because each side begins to treat the other as a threat. Skeptics fear gullibility, believers fear dismissal. Once fear enters, the goal stops being understanding and becomes winning. We refuse caricature because both fears have roots. Archaeologists have seen frauds, misdated objects, and motivated readings that collapse under basic checking. They have watched spectacular claims fade when samples are retested, or when a context turns out to be disturbed. Caution becomes a survival trait in a field where one error can stain a career. Alternative researchers have seen real arrogance, real gatekeeping, and real cases where early dismissal delayed better questions. They have watched experts speak with certainty, then revise quietly when new data arrives. The wound is not imaginary. Even when the conclusions are wrong, Extraordinary claims require extraordinary support, and that phrase is often weaponized. It should not mean impossible. It should mean the evidence must be strong enough to overcome prior probability. In other words, the more a claim rewrites the map, the more clearly it must show its coordinates. Prior probability is not prejudice, it is a baseline. If a claim implies a missing industrial ecosystem, then we should expect traces, and we should demand a search strategy. Advanced methods tend to leave footprints: waste products, tool fragments, standardized blanks, and distribution networks. If those footprints are absent, the claim must explain the absence, not ignore it. We call back to the drill core mystery because it is the perfect example. A dramatic spiral striation can be real, yet it can also be lighting, damage, or selective presentation. A spiral can emerge from a hand-driven drill with abrasive slurry because grit cuts in tiny jumps and rotation creates a helix. The question is not whether spirals exist, but what their pitch, depth, and consistency actually measure. The dispute is not settled by a single photograph. It is settled by sampling, measurement, and publication of the full distribution, including boring examples that do not go viral. If only the most dramatic hole is shown, the audience never learns what normal looks like. Without a baseline, every outlier becomes a prophecy. Cherry-picking is the first cognitive trap, and it is easy to do without lying. You show the tightest joint, the cleanest hole, the sharpest edge, and you imply the whole site matches. The camera can make a monument look perfect by refusing to show the chipped corners and patched faces. A site is a population, not a postcard. Argument from incredulity is the second trap, and it is emotionally persuasive. If I cannot imagine the method, then the method must not exist, and imagination becomes a false instrument. Human intuition is poor at scaling effort across decades because we live in short projects and short attention spans. What seems impossible in a weekend can be routine across a lifetime. Anomaly-driven storytelling is the third trap, and it is the most seductive. You collect puzzles, you stack them, and the stack feels like a pattern even when the base rates are unknown. A few unusual blocks can dominate the narrative, even if thousands of ordinary stones surround them. The mind confuses memorable with representative, and the story hardens. The mind loves mystery because mystery feels like depth. Yet depth without method becomes a hall of mirrors, where every unknown is treated as evidence for the same conclusion. If everything is a clue, then nothing can falsify the theory, and unfalsifiable claims become immune to learning. Mainstream caution has its own traps. Overconfidence in established chronologies can harden into reflexive dismissal, especially when a claim arrives with a hostile audience. When experts feel attacked, they may defend the boundary instead of investigating the anomaly. The result can be a missed opportunity to refine the story. Institutional risk aversion is not always corrupt, but it is real. Careers are built on stable interpretations, and instability can feel like personal attack. Funding committees often prefer safe questions with predictable outcomes, because failure is expensive. That pressure can narrow curiosity, even when curiosity is deserved. Now we widen the stakes beyond method, because the debate carries cultural weight. Monuments are not neutral. They are used to anchor identity, pride, and belonging. A stone wall can become a national symbol, and symbols attract battles that have nothing to do with stone. Colonial legacies still haunt the conversation. For centuries, outsiders claimed that indigenous peoples could not build what they built, and those claims justified domination. In the 19th and early 20th centuries, mysterious builders became a convenient myth, because it made conquest feel like stewardship. The camera shows old engravings and museum labels, language that praises the monument while erasing the makers. So when someone says they couldn't have done it, it is not a technical statement. It echoes an old erasure, even when the speaker thinks they are only being logical. The phrase carries a history of being used against living communities, not just against the dead. That is why the reaction can be fierce, and why the debate can ignite. The ethical dimension is unavoidable. Crediting ancient peoples is not charity. It is accuracy, because ingenuity is a human constant, not a modern monopoly. Skill accumulates when training is systematic, and societies can institutionalize technique through apprenticeship, standard measures, and shared templates. Alternative narratives sometimes repeat the same erasure in a new costume. Outsiders, Atlanteans, or visitors become the authors, and local builders become labor without agency. The story keeps the monument impressive, but it relocates intelligence elsewhere. Ask yourself what is being protected, wonder or hierarchy. Yet mainstream narratives can also erase in a quieter way. When craft is reduced to brute labour, the intelligence of technique disappears and the people become a workforce, not engineers. A lever is not just a stick, and a ramp is not just a pile of dirt. They are components in a system of planning, measurement and quality control. We keep the frame balanced. The question is not whether ancient people were brilliant. The question is what mechanisms produced consistent precision at scale. Precision is not a miracle, it is a habit, built from standards, feedback, and the ability to detect small errors before they compound. That brings us back to standards of evidence, because standards are the bridge between awe and explanation. A standard is not a wall, it is a shared language for disagreement. Without standards, the loudest voice wins, and the stones become props. Stratigraphy tells us when. Tool marks suggest how. Experimental replication tests whether the how can actually reach the observed tolerances. The camera alternates between a trench profile and a macro shot of a worked surface, where tiny grooves run like frozen motion. Each groove is a record of contact, tool against stone, abrasive against mineral grains. Context tells us whether an object belongs to the claim being made. A drill hole in a reused block is not the same as a drill hole sealed in an original construction layer. If a later culture reworked an older stone, the marks tell two stories at once. Sorting those stories requires patience, not certainty. Replication must include failure rates, because real craft includes breakage. A demonstration that only works once is not a workflow, and monuments are workflows made visible. In real production, tools dull, abrasives vary, and operators make mistakes, then correct them. The correction process is often where the technique reveals itself. We address the hide narrative directly, because it is the chapter's title pressure. What is actually documented publicly is larger than most viewers realize. There are site reports, measured drawings, petrographic studies, and radiocarbon datasets that never become headlines. The problem is not total absence, but uneven visibility. Excavation reports, catalogues, and survey data exist, yet they are fragmented. They are scattered across institutions, languages, and decades of publication norms. Some are printed in small runs, and some were never digitized, which makes them effectively invisible to a global audience. A fact that cannot be found might as well not exist. What is alleged is a coordinated suppression of decisive evidence. That allegation requires its own evidence, because coordination is hard and leaks are common. Large conspiracies are noisy, because people disagree, retire, and talk. To claim silence, you must explain how silence is maintained across generations. Still, secrecy can be simulated by ordinary dysfunction. Underfunded museums restrict access. Conservation limits handling. Political instability locks archives. A civil conflict can close a research centre for years, and a single broken climate control system can halt study of fragile pieces. Even photography policies can look like censorship. Sometimes they protect fragile surfaces, sometimes they protect revenue. Either way, the result feels like a closed door. When a visitor is told no flash or no close-ups, suspicion can bloom in the space where explanation should be. We show how mistrust grows in that gap. When access is limited, people assume the worst. When people assume the worst, institutions become defensive and the loop tightens. The tragedy is that both sides can be acting rationally inside their own fears. Now we ask what would actually settle disputes, because the film is not here to farm conflict. It is here to turn conflict into a measurement program. The goal is not to humiliate one camp, but to replace arguments with datasets that both camps can interrogate. Better measurements come first because many claims are still qualitative. Flatness, squareness, roundness, and toolmark pitch can be measured, and measured beats argued. A surface that looks flat can be mapped into deviations, showing whether it is truly planar or only visually convincing. A joint that looks perfect can be quantified by gap width along its length. Open datasets come next, because trust follows transparency. If scans and raw numbers are public, then independent analysts can test claims without joining a tribe. Open data also reveals uncertainty, which is not weakness but honesty. When error bars are visible, exaggeration becomes harder. High-resolution scans are the practical tool for this moment. Photogrammetry, structured light, and laser scanning can capture surfaces at sub-millimeter detail and preserve them against loss. The visuals turn clinical, point clouds blooming into meshes, then into color maps of deviation. A stone becomes a landscape and every ridge becomes measurable. Toolmark databases are the missing bridge between craft and inference. If we catalogue marks from known tools and abrasives, we can compare ancient surfaces to controlled reference sets. Different abrasives fracture differently, and different stones respond with different textures. A database turns it looks machined into its groove spacing matches this process within this tolerance. Transparent experimental protocols are the final piece. Experiments must publish materials, grit sizes, pressures, stroke counts, and operator skill level, because hidden variables create false victories. A copper tube drill with quartz sand behaves differently than one with corundum, and water content changes cutting efficiency. Without protocol detail, replication becomes theatre. This is where the earlier chapters converge. Drill core claims need systematic sampling. Transport claims need route models and friction tests. Polygonal fitting needs documented iteration cycles. The point is not to deny difficulty, but to map difficulty into steps that can be tested. We also need to separate two questions that are often fused. One question is whether a method is possible. The other is whether it was used, at that site, in that period. Possibility is physics. Usage is history. Possibility without context becomes fantasy. Context without possibility becomes dogma. The only stable ground is where both meet. That meeting point is where the story stops being a belief and starts being an explanation. We return to diffusion versus convergence, because it shapes how people interpret similarity. Similar solutions can spread by contact. Similar solutions can also emerge independently under shared physics. When heavy stone must resist gravity, certain geometries keep appearing because gravity does not negotiate. The Mediterranean showed convergence under mass and stability. Peru showed convergence under seismic risk and interlock. Egypt showed convergence under metrology and state-scale coordination. In each case, the constraints differ, yet the results can rhyme, because humans learn, iterate, and copy what works. The camera crossfades between sites, letting the eye notice both resemblance and difference. None of that requires a hidden machine, yet none of it forbids a surprise. The point is to keep the door open, without letting the door become the evidence. Skepticism is not cynicism, and openness is not surrender. Now we name the human desire that fuels every forbidden story. Mystery feels like meaning. If the past is too solvable, then it feels smaller, and people resist that shrinkage. But why should solvable feel small, when solvable still required lives of labour and minds of discipline? But solvable does not mean unimpressive. A simple tool used with discipline can outperform a complex tool used carelessly, and monuments reward discipline. Precision can be achieved by repetition, checking, and correction, the way a musician finds perfect pitch through practice. The stones may be less like machines, and more like instruments. The most forbidden engineering may not be a hidden machine, it may be a forgotten respect for craft, where time, measurement, and materials are treated as sacred. Imagine a culture where tolerances are taught like prayers, and where the work is inspected not once but constantly. In that world, the miracle is not technology, but commitment. We end by changing the lens, because the next chapters need a new kind of proof. To move forward, we treat monuments as data, not as symbols. That shift does not drain the wonder, it sharpens it. Because numbers can reveal patterns the eye misses. Enter modern measurement and simulation. If the stones are an argument, then the next step is to read their numbers and let the numbers speak. The final images are quiet and luminous, scanners sweeping, grids forming, and ancient surfaces becoming maps of human intention. Some stones don't just sit in place, they seem to lock into reality with modern precision. Under hard sunlight, edges stay straight across meters, and joints read like ink lines drawn between blocks. For 8 chapters we argued over photographs, anecdotes, and instincts, because that is what the internet rewards. We chased the most dramatic close-ups, and we treated the cleanest corners like they were the whole story. Now we change the rules and treat monuments as data, because data can survive ideology. The central question stays fixed, even as the tools change. Do the world's most precise ancient stone monuments prove lost advanced engineering, Or do they reveal how much we underestimate human ingenuity, time, and technique? This chapter is the measurement chapter, where claims stop being vibes and start being numbers. It is also the chapter where awe becomes sharper, because precision can be described rather than merely admired. We begin with reality capture at scale, because scale is where myths hide. A single photograph can flatter a wall, but a full scan has to live with every bump. Terrestrial laser scanning sweeps a wall into a point cloud, and every point has a coordinate. The scanner emits pulses, measures their return time, and converts that timing into distance with known uncertainty. As the instrument rotates, the wall becomes a constellation of millions of points, cold, impartial, and surprisingly beautiful. Photogrammetry turns overlapping images into a mesh, and the mesh can be checked against control targets. The method is older than people think, rooted in 19th century surveying and refined through modern computer vision. It works by finding the same features across many photographs, then solving for camera positions and surface geometry. When done carefully, it produces a textured model that feels like you could touch it. When done poorly, it produces a convincing illusion that collapses under measurement. Structured light and handheld scanners fill in tight spaces, and the result is a surface you can revisit without returning. In narrow corridors and inside chambers, a tripod scanner may not fit or may miss angles. Handheld units project patterns, read their deformation, and infer shape at short range. The best projects combine methods because no single sensor sees everything. The monument becomes a dataset assembled like a mosaic, with each tile carrying its own accuracy. A scan is not a verdict because scanners have error budgets and failure modes. Reflective stone, deep shadows, and oblique angles can create noise that looks like tool marks. Dust, humidity, and heat shimmer can bend light and shift measurements by millimeters. Even the simple act of placing the tripod introduces risk, because a tiny tilt can bias an entire station. That is why calibration matters, and why control points and repeat passes matter. Control networks are the quiet backbone of credibility. Survey targets with known positions tie separate scans into one coordinate system. Repeat measurements reveal drift, and drift tells you when a dataset is lying. Registration algorithms can make two scans appear to align, yet still hide systematic error. The new archaeology is not just high-tech, it is documented uncertainty. In plain language, it is admitting what you do not know and showing your work. Once the geometry is captured, we measure what people argue about most. Flatness becomes a deviation map, where a face is compared to a best-fit plane. The output is not a single number, but a field of differences across the surface. A heat map can show whether a block bows outward, dips at the center, or twists at the corners. It can also reveal whether a perfect face is perfect only in the region the camera loved. Squareness becomes an angle distribution, not a single heroic measurement. Instead of one corner checked with a carpenter's square, we evaluate many corners across many blocks. We can compute the spread, the bias, and the pattern of deviation. If the angles drift in one direction, that suggests a consistent reference method. If they vary randomly, that suggests local fitting rather than standardized templates. Parallelism becomes a field of normals, showing whether a block is truly regular or only looks regular. Each tiny patch of surface has an orientation, and those orientations can be mapped. A face may be flat but slightly rotated, and that rotation matters for stacking and load paths. When two opposing faces are parallel within a tight tolerance, it implies deliberate control. When they are not, it implies the builders solved alignment in other ways, perhaps with bedding and shims. Joint gaps stop being a close-up mystery and become a measurable seam. We can compute gap width along an entire joint, not just at the photogenic corner. That means sampling every few millimeters, then plotting the results like a medical scan. A joint may be tight at eye level, then open slightly where no one looks. That is not a failure of craft. It is a clue about priorities. We can test whether a joint is face-tight but back open, which changes the labour story. A face-tight joint can be achieved by careful dressing on the visible edge while leaving relief behind. That relief can prevent binding during placement, and it can reduce the time needed to fit the stone. We can also detect shims, mortar traces, and later infill that photographs often hide. In the data, a thin wedge becomes a measurable geometry, not a rumour. Block geometry becomes a population, and populations reveal intent. A single block can be exceptional by chance, but 100 blocks form a pattern. If blocks cluster around standard sizes, that suggests templates and production routines. It hints at measuring rods, marking practices, and foremen who enforce consistency. If blocks vary wildly but joints remain tight, that suggests iterative fitting and local adjustment. If only a few blocks show extreme precision, that suggests showcase labour rather than universal machining. It may indicate ceremonial zones, entrances, or places where the builder's reputation mattered most. The monument becomes a map of attention, showing where time was spent. That map can be compared to visibility, access, and symbolism. Precision, in other words, can be social as well as technical. Now we return to the drill core mystery with the tool that ends arguments. High-resolution scanning inside holes can measure groove pitch, depth, and continuity. If the groove is truly helical, its pitch should be consistent, and its geometry should wrap around with predictable spacing. If it is a set of scratches, it will wander, break, and change character. The difference is not philosophical, it is measurable. Microscopy can distinguish true helical striations from weathering curves and restoration scratches. Under magnification, the edge of a groove has a story, because cutting and abrasion leave different microtopographies. A rotating drill with abrasive slurry tends to leave rounded, smeared textures with aligned micro-scratches. A later steel tool can leave sharper, more brittle microchipping. Even the direction of micro-scratches can indicate motion, like wind lines frozen in stone. Large sample measurement can show whether extreme feed rate claims are common, rare, or misread. A claim about advanced drilling is not proven by one spectacular example. It must survive statistics because real technologies leave repeatable signatures. If a method is fast, it gets used often, and often leaves a distribution of similar marks. If it is rare, it may be a special case, an experiment, or a later intervention. The key is sampling discipline, because outliers can dominate belief. We scan boring holes as well as famous holes, and we publish the full distribution. That includes the ugly holes, the broken edges, and the ones no one posts online. If the dramatic spirals are consistent across many holes, then our models must explain that consistency. If they are rare and contextually messy, then the claim weakens without anyone needing to win a culture war. Microscopy is the next lens, because stone remembers contact at the micron scale. Under magnification, abrasion leaves oriented micro-scratches and a smeared texture that tracks grit movement. Pecking leaves impact pits with crushed grain boundaries and radiating microfractures. Chiseling leaves step fractures and edge chatter that can be compared to experimental reference marks. In plain terms, the surface is a diary, and microscopes let us read smaller handwriting. Surface analysis also reveals the enemy of clean inference. Later restoration can introduce modern abrasives, rotary tools, and polishing compounds that mimic ancient smoothness. Cleaning can erase weak tool marks and leave only the strongest ones, which biases interpretation. Even biological growth can etch patterns that look intentional under raking light. Lichens, salts, and water films can create textures that imitate human work with unsettling accuracy. So we build a reference library, because interpretation needs baselines. We cut and grind test stones with copper, bronze, stone pounders, and abrasive slurries. We record grit size, water content, pressure, stroke count, and operator skill level. We document how the marks change as tools wear and as grit breaks down into finer particles. We then compare ancient surfaces to known signatures, because looks machined is not a measurement. Experimental archaeology has a history here, and it is not new. For more than a century, researchers have tried to replicate ancient finishes with plausible tools. What changes now is the instrumentation, because we can quantify roughness, directionality, and microfracture patterns. We can also archive the results, so future teams can recheck them. The goal is not to perform a stunt, but to create a controlled comparison. Now we add geology, because stone is not interchangeable. Petrography identifies mineral composition and grain size, which control how a surface fractures and polishes. Granite, for example, is a mosaic of minerals with different hardness, and that mismatch affects how it abrades. Fine-grained stone can take a uniform polish, while coarse-grained stone can tear and pit. A finish that looks impossible on one stone can be routine on another. Hardness mismatches matter differently in fine-grained granite than in coarse granite. Quartz resists abrasion, feldspar can cleave, and mica can smear into reflective planes. Under a microscope, those minerals reveal whether a surface was ground, pecked, or naturally weathered. The same tool can behave differently depending on grain size and cementation. Geology is not a footnote, it is the medium that sets the rules. Sourcing turns romance into logistics. Geochemical fingerprinting can link blocks to specific quarries using trace elements and isotopes. Small variations in chemistry act like a barcode, especially when combined with petrographic texture. When a wall stone matches a distant source, the transport problem becomes real and countable. When it matches a nearby outcrop, the story shifts toward local organization and repeated practice. Transport distance is not just a number, because distance implies infrastructure. Long hauling implies roads, staging areas, seasonal planning, and replacement tools. It implies a supply chain for food, rope, timber, and abrasives. It implies people whose job was not carving, but coordinating. If the quarry is far, the monument is also a map of administration. Historical context matters here, because ancient states often measured power through logistics. In Egypt, quarrying and transport were tied to centralized authority, written records, and organized labor. In the Andes, labor obligations and seasonal work could mobilize thousands with remarkable efficiency. None of that requires machines that vanish without trace, yet it does require social systems that modern viewers rarely imagine. The stones may be silent, but the logistics behind them were loud. Geology also tests diffusion versus convergence without speculation. If distant sites use similar stone types and similar abrasive sources, similarity may be convergent physics. If they use different stones but similar finishing signatures, similarity may be shared technique. Either way, the claim becomes testable rather than tribal. The argument moves from "they must have had the same secret" to "their constraints produce similar solutions." Now we move from surfaces to forces because monuments are also structures. Finite element analysis turns a wall into a model with material properties and contact conditions. The model divides stone into many small elements, then solves how stress and strain distribute under load. We can simulate gravity loads, settlement, and lateral shaking, then compare predicted failure modes to real cracks. Simulation does not replace fieldwork, but it can falsify lazy stories. Material properties are not guesses when measured carefully. Stone has compressive strength, tensile weakness, and anisotropy that depends on bedding planes and microcracks. Contacts between blocks can be modelled with friction, cohesion, and gap behaviour. Even small assumptions can change outcomes, which is why transparency matters. A model is not a magic oracle. It is a disciplined way to ask, if this is true, what should we see? Polygonal masonry is the perfect case for this, because it is both aesthetic and mechanical. Interlocking blocks distribute stress across many contacts, and they resist sliding under lateral loads. Small rotations can be accommodated without catastrophic collapse, which matters in seismic zones. The joints look like art, yet they also behave like engineered interfaces. The question is not whether it looks clever, the question is whether it performs as claimed. Seismic simulation can test competing hypotheses about why the joints are shaped. If performance improves mainly from block weight and batter, then the joint complexity may be partly cultural display. If performance improves mainly from interlock geometry and contact area, then the complexity has a structural payoff. We can vary friction, gap tolerance, and block arrangement to see what actually matters. We can also test whether failure begins at corners, at mid-joint, or at foundation interfaces. We also test the claim that extreme precision is required for seismic performance. Models can explore how much gap can exist before sliding begins, and how much irregularity can be tolerated. If performance remains strong with millimeter-level gaps, then razor joints may be overkill. If performance collapses with small gaps, then precision becomes a functional necessity. Either result is informative because it connects craft to physics. Now we use scans to reconstruct construction sequences, because sequence is where human choices appear. In some sites, scan data reveals levelling courses, packing stones, and hidden adjustments behind perfect faces. Behind a clean facade, there may be rough backs, chock stones, and void-filling rubble. That does not diminish the achievement. It shows practical thinking. It shows builders solving problems with the materials they had. In others, scan data reveals that faces were dressed after placement because tool marks cross joints. A chisel line that runs uninterrupted from one block to the next implies finishing in situ. That suggests scaffolding, access planning, and a willingness to refine after the heavy lifting. It also suggests inspection. because someone had to decide when good enough became done. Sequence can show whether blocks were pre-finished in a yard or tuned in place. Case studies sharpen the stakes because they show both clarity and surprise. At some Egyptian sites, scans confirm that many joints are tight only where they are visible and relieved where they are hidden. That pattern supports labour allocation and quality control, not universal machining. It also matches what we know about ancient project management, where symbolic surfaces receive disproportionate attention. Yet in other zones, the measured flatness and alignment are so consistent that they demand disciplined metrology. That metrology does not require lasers, but it does require standards. Straight edges, plumb lines, water levels, and simple squares can produce impressive results when used relentlessly. Repeated checking creates a feedback loop, where small errors are corrected before they accumulate. The scan can reveal that loop indirectly, because the error patterns become systematic rather than chaotic. When deviations cluster tightly around zero, someone was policing the work. In Peru, scans can reveal whether contact surfaces are truly full contact or only edge contact. They can show whether the interlocks are continuous or interrupted by small voids. They can also reveal whether perfect joints are partly the result of later settling that close gaps. Settlement can tighten joints in some places while opening them in others, and the pattern can be mapped. Each outcome changes the story without reducing the awe. The visual impact of these datasets is its own kind of revelation. A polygonal wall becomes a coloured topographic map, with reds and blues marking microns of deviation. A joint becomes a graph, rising and falling like a heartbeat along its length. You can watch a block's face transition from rough to refined, as if the stone carries a memory of the last passes. The monument stops being a postcard and becomes a measured landscape. In the Mediterranean, reality capture can expose quarry-to-wall continuity. Tool marks on unfinished faces can be matched to quarry scars, linking workflow steps. Standardized lifting bosses and drafted margins can be measured across blocks, revealing whether a site used templates. When recurring dimensions appear, they hint at shared tools and shared training. The point is not to declare a single method, but to map variation into a coherent process. Now we confront the ecosystem challenge from the drill core debate, because measurement makes absence visible too. If high-speed mechanized drilling existed, it should leave consistent geometry, consistent wear signatures, and consistent byproducts. It should also leave hardened components, bearings, power transmission traces, and workshop debris clustered near production. We can search for those traces with the same rigor we apply to grooves. We can also ask where the waste went, because industrial work produces industrial leftovers. So far, the ecosystem evidence remains thin and uneven, and that matters. A technology that can drill granite at industrial rates usually spreads and standardizes because it saves time. It creates training traditions, spare parts, and repair waste that accumulates in the ground. It tends to leave a signature in settlement patterns, tool caches, and supply networks. If those patterns are missing, the advanced machine claim must explain why. But we also admit what measurement cannot do alone. A scan can tell you a surface is flat, but it cannot tell you who enforced the standard. A simulation can show a wall resists shaking, but it cannot tell you who decided to build that way. Numbers can narrow possibilities, yet they cannot supply motives. After measurement comes meaning, and meaning returns us to people. Now we name the new possibility that modern tools unlock. Open science can turn monuments into shared datasets, where anyone can test claims without joining a camp. Raw point clouds can be published with metadata, control networks, and error estimates. Toolmark micrographs can be archived with scale bars and provenance. Structural models can be shared with assumptions exposed, so disagreement becomes parameter changes instead of insults. This is not a utopia, and it has practical constraints. Cultural heritage laws, site access, and the risk of looting complicate what can be released. Data files are enormous, and long-term storage is not glamorous work. Yet the direction is clear, because transparency changes incentives. When methods are visible, the loudest voice has less power. Reproducible measurement changes the debate's incentives. If a claim can be checked by independent teams, then charisma matters less than calibration. If a dataset includes the ugly stones as well as the perfect stones, cherry-picking becomes harder. If uncertainty is published, then exaggeration becomes visible, and visible exaggeration loses power. The argument becomes a contest of models, not a contest of personalities. This is why the chapter is a climax even without a single shocking reveal. The reveal is methodological, because it changes what counts as evidence. The stones stop being props in a culture war and become instruments that record work. The mystery does not vanish, but it becomes bounded. The range of plausible stories narrows, and the remaining questions become better questions. The more we measure, the more nuanced the story becomes. Some impossible claims weaken when gaps, repairs and selection bias are quantified. Some claims sharpen into real research questions when precision is confirmed across large samples. The past becomes less magical in one sense, and more impressive in another. It becomes impressive in the way a long, disciplined project is impressive. We return to the opening hook and translate it into a testable statement. If surfaces whisper of machining, we can measure surface roughness and directionality. If joints admit no blade, we can map gap distributions and contact patterns. If drill holes imply high feed rates, we can measure groove pitch and compare to experimental drilling under known pressures. The point is not to win a debate, but to constrain reality. Then we ask the harder question that numbers force on us. If advance does not require lost machines, what does it require? It requires time budgets that modern minds resist, because we live in short cycles. It requires training systems that turn bodies into instruments, and inspection routines that catch errors early. It requires administrators who treat tolerances as policy. It also requires a cultural reason to care, because precision is expensive. Monumental projects often served religion, legitimacy and memory, which can justify costs that markets would reject. A society can choose to spend years perfecting stone because the stone is not only material, the stone is a contract with the future. When you stand before it centuries later, you're reading the terms, so the forbidden engineering may be hiding in plain sight. It may be the disciplined feedback loop of craft, where measurement is constant and correction is expected. It may be the willingness to iterate until surfaces converge, using abrasives and simple gauges as the quiet engines. It may be the social machine that keeps standards alive across generations. If that is true, the technology is not a device, it is a system of behavior. We do not close the door on surprises because science should not fear being wrong. We simply raise the bar for what a surprise must look like in the ground. A lost machine would need a material ecology, a distribution pattern, and a reproducible signature. It would need to show up in more than one heroic artifact, and it would need to leave a trail of maintenance and waste. Without that, the strongest story is still human ingenuity under constraint. Now we set up the final chapter by narrowing the lens again. Measurement can tell us what was done, and sometimes how it was done. It cannot tell us what it meant to the builders, or why they accepted the costs. It cannot tell us what a perfect joint signified to a priest, a king, or a worker whose hands bled on stone. After measurement comes meaning, and meaning returns us to the human story. We end with the conclusion theme as a challenge that the data makes harder to dismiss. The most forbidden engineering may not be a hidden machine, but a forgotten respect for disciplined human craft. If that respect built these stones, then the real mystery is not lost technology. The real mystery is whether we still recognize devotion when it takes the form of precision. We return to Egypt, Peru, and the Mediterranean with one claim. Engineering is not only tools, it is organization, metrology, patience, and material mastery. In every quarry scar and chisel mark you can read a workflow, teams, schedules, inspections, and a shared idea of good enough. Precision can emerge from simple implements guided by abrasives and standards. Straight edges, plumbs, water levels, and gauges turn effort into repeatable tolerances. A plumb line makes gravity visible, and a water level makes horizontality portable across uneven ground. Even without modern steel, reference surfaces can be generated by rubbing, checking, and rechecking until high spots reveal themselves. Iterative workmanship matters most. Mark, remove, test fit, correct, then lock the result. The process is slow, but it is also self-correcting, because each pass carries the last error forward into the next measurement. This reframes advanced without shrinking the achievement. When we say simple tools, we do not mean simple outcomes. A copper tube can guide grit that cuts granite if feed and slurry are controlled. Quartz and sand become the true cutting edges, and the metal becomes a guide that keeps pressure and geometry consistent. A polygonal wall can be tuned by contact transfer, shims, and countless checks. You can imagine soot, pigment, or wet clay revealing touchpoints. Then a worker removes only what prevents full contact. A megalith can be moved by logistics that treat friction, timing and labour as equations. Rollers, sledges, wetting the path, and coordinated pulls turn raw strength into managed force. Yet some questions stay open, and they deserve better study. Drill core spirals need large sample pitch measurements, microscopy, and published uncertainty. Tool chatter, grit size, and variable pressure can all write patterns into stone, and we need to separate signal from coincidence. Scaling remains unclear. How many trained hands, how many failures, and what time budgets? A single perfect joint is impressive, but 1,000 perfect joints imply training systems, supervision, and replacement of broken tools. The record is incomplete through looting, reuse, restoration, and archives that remain hard to access. Stones migrate into later walls, and old surfaces get recut, blurring the original sequence. We also explain disappearance without invoking vanished superpowers. Craft dies when states fall, patronage ends, materials change, and apprentices scatter. When timber, copper, or abrasive sources shift, a proven method can become too expensive to sustain. Without written manuals, tacit knowledge can vanish in one generation. Technique lives in hands and eyes, then it is gone when the workshop dissolves. So we reject false certainty on both extremes. Do not dismiss anomalies as noise. Do not leap from anomalies to lost machines without an ecosystem of traces. If a method existed at scale, it should leave consistent debris, tool wear, and a chain of intermediate attempts. The monuments become time machines. They prove intelligence and ambition are ancient constants. Under starlight, tight-fitting stones hold their line, engineering as memory carved into earth itself. And the quiet question lingers. If skill can build this, what else could skill explain, if we measure carefully enough? We followed seams that vanish, faces that stay flat across meters, and stones so heavy they turn landscapes into construction sites. We tested each wonder against materials, tool marks, transport, and metrology, learning that precision is not a vibe but a measurable discipline. And when the debate tightened around granite drill holes and spiral striations, we found the real battleground was evidence itself: sampling, context, replication, and the missing ecosystem any true machine age should leave behind. Egypt showed us how hardness changes everything, and how abrasives can make copper a guide while grit becomes the cutting edge. Peru showed us joints that behave like mechanisms, not because they were magical, but because they were checked, corrected, and checked again until geometry became seismic insurance. The Mediterranean giants widened the pattern, hinting that similar solutions can emerge wherever mass, gravity, and ambition collide, through diffusion, convergence, or both. By the end, lasers and simulations did not kill the mystery, they refined it, turning folklore into tolerances and turning arguments into datasets. Some questions remain deliberately open, because they deserve better than certainty made from screenshots. Are the most dramatic drill spirals consistent across large samples, or amplified by lighting, damage, and selective presentation? If high-speed mechanized drilling ever existed, where are the bearings, hardened parts, workshop debris, and standardized wear signatures that should cluster around it? And if disciplined craft is the answer, how did ancient states train, inspect, and sustain quality at city scale, across thousands of stones, across generations of hands? So who taught Bronze Age hands to build like this? Lost engineering they tried to hide, or a human technique so advanced we've forgotten how to see it? After all we've measured, the more forbidden possibility is not a secret machine, but a public method, time, standards, and relentless checking, treated as sacred enough to outlast empires. The stones may remember a blueprint, but the blueprint could be social, a culture of measurement that made patience into power and craft into law. What if the real scandal is not that the past had impossible technology, but that we have made their possible technology feel impossible by forgetting the cost of mastery? In the end, these monuments do not ask us to believe in hidden engines. They ask us to respect what humans can do when they refuse shortcuts, and when precision becomes a form of devotion. If we want the argument to end, we have to earn the ending. Measure more, publish openly, replicate honestly, and let the stones speak in numbers.